Florida is home to the most ambitious engineering feats in the United States. From soaring towers to sprawling transit systems, these megaprojects are redefining the state's skyline. In this video, we explore the biggest construction efforts transforming Florida's future, massive in scale and groundbreaking in every sense. With the latest additions to the landscape of modern entertainment engineering, Universal Orlando's Epic Universe stands as a formidable example of how large-scale theme park development pushes the boundaries of construction logistics and immersive design. Conceived as an expansive new addition to the Universal Orlando Resort, the project required the transformation of over 700 acres of previously underutilized land into a fully integrated theme park environment. The initial phases of the project began with comprehensive site surveying, geotechnical analysis, and land clearing. Crews needed to regrade vast swathes of land to ensure proper drainage and structural stability. Underground utilities, including high-capacity stormwater management systems and electrical conduit networks, were laid out early in the process to avoid costly rework during vertical construction. To accommodate the multi-gate layout, civil engineers mapped out internal roads, pedestrian paths, and backstage support corridors, all designed to handle the anticipated heavy volume of guests and service vehicles. A series of massive retention ponds were excavated not just for water management, but also to act as visual and thematic barriers between different park zones. Construction staging areas were carefully allocated at various nodes around the site, enabling multiple trades to work simultaneously on the various themed lands. Structural frameworks for each land within the park varied significantly depending on the thematic and functional requirements. Steel-framed show buildings featuring complex soundproofing and HVAC systems were erected using tower cranes and prefabricated panel systems. Foundations had to be over-engineered in certain zones to support the enormous static and dynamic loads associated with ride systems, many of which rely on high-speed launches, track-switching mechanisms, or deeply embedded hydraulic lifts. In some attractions, such as those simulating flying or space travel, vibration isolation pads were incorporated beneath the concrete slabs to prevent mechanical resonance and structural fatigue. Mechanical integration posed a particular challenge given the density of infrastructure. Each attraction required its own climate control, power supply, data networking, and life safety systems. Fire suppression, especially in dark ride environments, had to meet stringent code requirements while remaining concealed within themed architecture. Likewise, air handling units were often buried underground or hidden in faux architectural elements to preserve the illusion of immersive storytelling. Exterior theming was a collaborative effort between construction teams, scenic artists, and rockwork specialists. Shotcrete sculpting was extensively used to fabricate mountains, castles, and alien landscapes. Fiber-reinforced polymer cladding was applied to facades for lightweight but durable finishes. Paint crews worked alongside sculptors to apply multi-layered coatings that would resist Florida's intense UV exposure and frequent rainfall. A particularly sophisticated aspect of the project involved park-wide integration of a digital experience layer, necessitating deep trenching for fiber optic cabling and distributed antenna systems. This infrastructure underpins everything from mobile app-based ride reservations to location-aware character interactions. Beneath the surface of Biscayne Bay, the Port of Miami Tunnel represents one of the most complex underwater infrastructure undertakings in the southeastern United States. Constructed to alleviate downtown Miami's chronic congestion caused by thousands of daily truck trips to and from the port, this project required advanced tunneling methods, massive marine coordination, and exacting safety systems. The overall plan was to connect the MacArthur Causeway directly to Port Miami via twin tunnels, each approximately 3/4 of a mile in length, buried beneath the seabed and designed to handle bidirectional vehicular traffic. Before tunneling could begin, preparatory works focused on dredging and stabilizing the soft bay soils. Extensive geotechnical investigations were conducted using boreholes and cone penetration tests to classify the variable limestone and sand strata that would be encountered. Ground improvement methods such as jet grouting and ground freezing were considered in preliminary phases, but the design ultimately relied on a pressurized face tunnel boring machine capable of navigating both soft ground and denser rock formations. Custom-built in Germany and shipped in segments, the TBM used on this project was over 40 feet in diameter and weighed several hundred tons. Assembly took place in a large launching pit on Watson Island, where reinforced concrete diaphragm walls and a trimmy-placed base slab formed the structural cradle. The boring process progressed incrementally, with the TBM advancing just a few feet per hour while simultaneously installing precast concrete segment rings behind it to form the tunnel lining. These segments, fabricated off-site and transported to the launch area, were equipped with waterproof gaskets and dowel interlocks to ensure tight seals under hydrostatic pressure. The tunnel alignment passed beneath the shipping channel, which introduced unique challenges related to buoyancy, water ingress, and structural reinforcement. At the deepest sections, the tunnel crown lay more than 100 feet below the water surface. To resist both groundwater pressure and seismic loading, the tunnel lining thickness and steel reinforcement were increased, especially at the crown and invert where stress concentrations were highest. Real-time instrumentation inside the TBM provided feedback on ground conditions, face pressure, and segment placement accuracy, helping to mitigate risks of sinkholes or blowouts. Simultaneously, surface-level works included the construction of ventilation buildings at each portal. These reinforced concrete structures house massive axial fans, emergency backup power systems, and life safety controls. Each tunnel is equipped with a full suite of fire suppression systems, including deluge sprinklers and fire-rated wall finishes. A network of electronic signage, CCTV, and incident detection sensors runs the entire tunnel length, all connected to a centralized control room staffed continuously. Upon completion of tunneling, crews moved on to road deck construction, lighting installation, and system commissioning. Pavement was laid using specialized low-sag asphalt mixes designed to withstand constant vehicle loading in a confined environment. Final testing included simulated fire events, emergency evacuation drills, and full-scale load testing to ensure operational readiness. Breaking ground on what is envisioned to become the largest retail and entertainment complex in North America, American Dream Miami is a mega project that combines commercial ambition with vast construction scale. The site, spanning several hundred acres in northwest Miami-Dade County, required extensive groundwork before vertical construction could even be considered. Initial site development involved substantial clearing and grubbing of existing vegetation, followed by the removal of unsuitable soils and replacement with engineered fill. Soil compaction and moisture conditioning were conducted systematically, zone by zone, to meet strict geotechnical specifications given the project's susceptibility to high water tables and the underlying karst limestone. Stormwater management was one of the most critical challenges from the onset. Crews installed a comprehensive drainage network composed of perforated HDPE pipes, catch basins, and retention ponds to control runoff during South Florida's intense rainfall events. Because of the site's proximity to sensitive wetlands, strict environmental controls had to be maintained throughout construction. Silt fences, turbidity barriers, and regular environmental monitoring were deployed to ensure compliance with state and federal mandates. The primary structure of the complex comprises a combination of reinforced concrete and structural steel, chosen based on load distribution needs and span requirements. While concrete forms the foundation mat and shear walls, wide-span areas such as the indoor ski slope, water park enclosure, and retail atriums utilize steel framing with long-span trusses and moment connections. The ski slope, one of the central engineering feats, requires a climate-controlled interior envelope over several hundred feet long, with complex thermal insulation and vapor barrier systems. The structural shell is thermally isolated from the surrounding environment, using insulated metal panels and a controlled HVAC system designed to maintain sub-freezing temperatures in a tropical climate. Mechanical, electrical, and plumbing coordination was a substantial portion of the build process, with extensive BIM modeling used to resolve spatial conflicts in densely packed service corridors. Chilled water systems, electrical bus ducts, and fire sprinkler mains all had to be routed through the superstructure without interfering with visitor circulation, escalator shafts, or themed architecture. Substations and cooling towers were strategically located in peripheral service yards to reduce ambient noise and heat near visitor zones. Specialized foundations were needed in areas designated for amusement rides, where dynamic loads exceeded standard building tolerances. Engineers embedded deep auger cast piles beneath the footings to transfer those loads to stable substrata. Vibration isolation systems and seismic expansion joints were installed at strategic intervals to ensure ride safety and structural resilience. Exterior construction involved a layered system of weather-resistant barriers, rain screen cladding, and themed facades that change appearance depending on the function of each zone. Materials ranged from precast concrete panels to architectural glass and high-pressure laminates. For the water park roof, translucent ETFE panels were chosen to allow natural light while minimizing solar heat gain, thereby enhancing energy efficiency. Rebuilding from near-total devastation, the reconstruction of Tyndall Air Force Base following the impact of Hurricane Michael in 2018 required a complete reimagining of military infrastructure in the face of extreme climate events. The project began with an intensive demolition and debris removal phase, where thousands of tons of structural wreckage, downed trees, and contaminated materials were cleared using heavy equipment including hydraulic excavators, high-reach loaders, and roll-off trucks. Before any vertical construction resumed, environmental remediation teams had to address storm-related hazardous material spills and groundwater contamination risks. Once the site was stabilized, the reconstruction effort shifted toward creating a base of the future, grounded in resilience, energy efficiency, and smart infrastructure. One of the foundational strategies was the implementation of mission-driven zoning, in which facilities were grouped by operational function: flight line, support, administrative, residential, allowing for optimized utility distribution, vehicular movement, and force protection measures. Civil engineers realigned roadways, constructed new perimeter security systems, and raised the elevation of key buildings to avoid future storm surge damage. The new construction used tilt-up concrete panels and hurricane-rated curtain wall systems across most structures. Load-bearing walls were designed to resist sustained winds exceeding 180 miles per hour, and all roofs were anchored with enhanced uplift connectors and continuous load paths to transfer forces to the foundation. Building envelopes included closed-cell spray foam insulation and thermally broken aluminum fenestration systems to improve energy performance while maintaining blast resistance in mission-critical zones. A major focus of the reconstruction was integrating advanced electrical microgrid systems. Redundant power generation sources, including solar PV arrays, diesel generators, and battery storage, were installed to ensure operational continuity during grid outages. Subsurface duct banks were rerouted and reinforced to improve storm resilience, and switchgear facilities were elevated above base flood elevation to avoid future water intrusion. Hangar complexes for F-35 aircraft required particularly high-precision construction tolerances. These steel-framed structures incorporated massive rolling hangar doors, anti-static flooring systems, and integrated fire suppression systems specifically engineered for jet fuel hazards. Mechanical systems included custom air handling units with high filtration capabilities to protect both personnel and aircraft maintenance environments. Drainage was redesigned with sustainability and resiliency in mind. Bioswales, reinforced outfalls, and permeable pavements were incorporated to improve stormwater quality and reduce erosion. Stormwater retention basins were expanded and linked to smart monitoring systems that automatically adjust outflows based on weather forecasts and rainfall events. The reconstruction also deployed extensive building automation systems across administrative and housing facilities. Lighting, HVAC, and security systems are now centrally controlled and monitored, allowing real-time energy optimization and system diagnostics. Residential zones were rebuilt to meet LEED Silver and above standards, using impact-resistant windows, high-efficiency HVAC units, and low-flow plumbing fixtures. Amid Florida's subtropical flatlands, the construction of Babcock Ranch Solar Town set out to prove that sustainable urban planning and utility-scale renewable energy could coexist in a master-planned community from the ground up. The project began with a rigorous environmental assessment of over 17,000 acres, ensuring that the development footprint would minimize disruption to existing wetlands and wildlife corridors. Extensive hydrological modeling was undertaken to manage the region's natural water flow patterns, with key areas set aside as conservation zones and integrated into the town's stormwater infrastructure. Once the primary civil grading was complete, roadways, utilities, and fiber optic communication lines were laid in tandem using a trench and backfill system coordinated through GPS-enabled machine guidance. Electrical distribution, unlike in most traditional developments, was built with solar generation as the core, not the supplement. Massive photovoltaic fields were constructed just outside the residential core, spanning hundreds of acres. The solar array used fixed tilt panels mounted on driven steel piles, with underground cabling channeling direct current electricity to inverters and step-up transformers before feeding into the regional grid. Residential construction throughout Babcock Ranch adhered to rigorous energy efficiency and wind resilience standards. Homes were built with insulated concrete form walls, impact-rated glazing, radiant barrier roof sheathing, and deep roof overhangs to mitigate solar gain. Roofing materials were chosen for their reflectivity and durability, including metal and tile products designed to exceed hurricane uplift requirements. Mechanical systems included high-SEER HVAC units, advanced dehumidification control, and smart thermostats integrated into home automation networks. What differentiated the town further was the full integration of microgrid technology. Battery storage facilities, housed in climate-controlled steel enclosures, provided grid balancing and backup capabilities. These systems ensured continuous power delivery even during grid disturbances and could island the town if necessary during extreme weather events. Switchgear, transformers, and substations were elevated on reinforced concrete pads with flood-proof enclosures and remote diagnostic sensors to prevent failure during high water levels. Public buildings and amenities, including schools, commercial centers, and community centers, were constructed using a design-build-delivery method to ensure consistency in green building standards and rapid delivery. All structures were wired for net metering, demand response control, and energy use feedback systems. Building envelopes featured continuous insulation, reflective membranes, and operable windows for cross-ventilation, where applicable passive cooling elements such as overhangs, louvers, and vegetative shading were incorporated into the architecture. Pedestrian infrastructure was planned ahead of vehicular design, with wide pathways, permeable paver systems, bioswales, and shade structures forming the connective tissue of the community. Stormwater is handled via a series of vegetated retention basins and interconnected canal systems, which serve dual purposes of flood mitigation and habitat support. Water and wastewater treatment systems were decentralized and included reclaim systems for irrigation, with smart meters installed throughout to promote conservation. Starting from its immense foundation work, the construction of Panorama Tower in Miami was an engineering endeavor that pushed the limits of vertical urban development in South Florida. The site preparation required the excavation of a deep foundation mat, nearly 10 feet thick, which would ultimately support the enormous structural loads of what became the tallest building in the state. The tower's foundation system relied on a network of auger cast piles extending more than 100 feet below grade, drilled through soft coastal sediments into underlying limestone strata. A high-strength concrete pour of over 13,000 cubic yards was executed in a continuous operation lasting more than 24 hours, involving dozens of concrete trucks in a carefully choreographed rotation. Once vertical construction began, the superstructure rose rapidly using a cast-in-place concrete core system. The central shear walls formed the backbone of the tower, housing elevator shafts, stairwells, and mechanical risers. Surrounding this core, post-tensioned concrete slabs and columns were poured in a cycle of roughly one floor every 4 to 5 days. To maintain this pace, formwork systems were mounted on self-climbing hydraulic jacks, and a just-in-time delivery system kept materials flowing without congesting the tight urban staging area. The building's mix of residential, commercial, and hotel uses demanded varied floor layouts and load-bearing considerations. Transfer girders, some spanning over 30 feet, were integrated at podium levels to redistribute structural loads around open lobby and amenity spaces. These massive concrete beams required temporary shoring towers and custom formwork assemblies, built and dismantled as the structure progressed upward. Mechanical systems throughout the tower had to account for vertical reach, energy efficiency, and hurricane resilience. Multiple chiller plants were stacked vertically at mechanical floors to optimize thermal load distribution. Water pressure zones were engineered using variable speed booster pump systems and brake tanks to maintain consistent pressure throughout the more than 80 stories. The electrical system incorporated dual feeds and emergency backup generation housed on elevated floors to avoid flooding risk. Vertical duct shafts were carefully coordinated with structural elements using 3D modeling tools to prevent clashes. The curtain wall system was engineered for high impact resistance and thermal performance. Each panel included laminated glass, extruded aluminum frames with thermal brakes, and anchoring systems rated for over 170 miles per hour wind loads. Installation occurred using mast climbers and swing stages, starting from the mid-tower levels and working both upward and downward. Balconies were constructed with cantilevered concrete slabs and glass railings carefully sloped to direct water runoff away from the facade. Elevator logistics were especially critical in such a tall structure. High-speed gearless traction elevators with destination dispatch were installed to minimize wait times, and reinforced machine rooms were positioned at intervals to house motors and control equipment. Fire protection systems included pressurized stairwells, zoned sprinkler systems, and smoke control fans, all tied into a centralized life safety command center. In the heart of downtown Miami, where the skyline rises in a collage of glass towers, 1000 Museum distinguishes itself not just by height, but by the extraordinary engineering involved in bringing its organic exoskeleton form to life. Long before any concrete was poured, the project demanded a fundamental rethinking of conventional tower design due to the decision to incorporate a curvilinear external structural system. The concept required that the building's primary structural support come from its exterior, a dramatic departure from the more common internal core and column system used in most residential high-rises. The foundation phase began with the installation of deep-drilled shafts extending over 100 feet into Miami's sedimentary bedrock. These shafts were reinforced with heavy steel cages and trimly poured concrete to form a stable load path beneath the structure's core and its unique perimeter support zones. Above ground, the ground-level mat foundation included thousands of cubic yards of high-strength concrete, placed in continuous pours to avoid cold joints and ensure structural uniformity. The mat, several feet thick, had to be completed in multiple stages, each meticulously scheduled to coordinate pump trucks, concrete deliveries, and rebar placement. As the became the central construction challenge. Rather than simple vertical columns, the perimeter frame was made up of sweeping biomorphic curves that branched and intertwined as they moved up the tower. This required a custom formwork system, fabricated off-site and assembled on-site in pieces, with tolerances often within a fraction of an inch. The forms had to be modified on a floor-by-floor basis due to the shifting geometries, and concrete placement was done in segments with continuous quality monitoring to prevent honeycombing or segregation within the curved shapes. The internal columns. Because the exoskeleton was exposed to the elements, its surface quality had to meet both structural and architectural criteria, requiring special attention during finishing, curing, and waterproofing. Inside the building loads at the highest elevation, along with wind load modeling to ensure rotor wash would not affect facade elements or roof equipment. Below the helipad, mechanical systems including chilled water plants and emergency generators were installed in hardened enclosures, isolated acoustically and vibrationally to avoid disturbing the building's luxury residential interiors. The glass curtain wall system was also a vital piece of the project. It had to be installed around the branching exoskeleton while maintaining weather tightness and minimizing air infiltration. Each panel was custom-shaped and tested for wind resistance, particularly given the building's exposure to hurricane-force conditions. Installation teams used specialized lifting rigs and sequencing plans to coordinate around the exoskeletal nodes, many of which intersected the glass modules in non-linear ways. Elevator and life safety systems at elevators and pressurized stairwells. The building featured advanced smoke evacuation systems and a full backup power architecture integrated into the overall structural system. From the foundation to the rooftop, every phase of the 1000 Museum's construction demanded attention to detail, precision, and innovative engineering. It stands not just as an architectural landmark, but as a testament to what is achievable when complex geometry, structural necessity, and construction craft are woven together into a seamless vertical composition. Few transportation projects in recent American history and heavily trafficked transportation zones. From the earliest design phase, engineers had to account for a range of technical challenges, from grade separation and drainage to layers and placing new continuous welded rail on concrete ties. The new track system was designed for higher-speed passenger operations while coexisting with freight rail, requiring the installation of upgraded ballast, drainage trenches, and reinforced embankments. Track geometry had to be carefully aligned to meet ride quality standards and minimize lateral forces at higher speeds. In contrast, the northern portion from West Palm Beach to Orlando International Airport involved new greenfield construction through undeveloped terrain. Crews cleared and grubbed hundreds of acres, rerouted surface water channels, and installed wildlife crossings in environmentally sensitive areas. Earthwork was extensive. Embankments and cut sections were designed to minimize gradients and allow for smooth acceleration and braking curves. The right-of-way was protected by a combination of fencing, access controls, and overpasses to eliminate at-grade crossings, critical for both safety and operational efficiency. Bridges and viaducts represented key components of the alignment, especially at major road crossings and river spans. Precast concrete girder bridges were deployed using accelerated bridge construction techniques. Piers were founded on deep-drilled shafts, many of which had to be constructed under challenging conditions involving soft soils and high groundwater levels. Certain elevated sections used segmental box girders cast in place and post-tensioned, allowing for long spans and reduced support footprint. These elevated guideways also helped mitigate environmental impact in flood-prone areas and reduce the need for extensive land acquisition. One of the most technically intensive elements was the implementation of a positive train control system across the corridor. This safety-critical layer included continuous GPS-based tracking, wireless communication between locomotives and control centers, and real-time enforcement of speed limits and signal compliance. Installation of the PTC system required the placement of signal houses, transponders, and fiber optic cable across the entire alignment, with redundant power sources and cybersecurity protections. The stations themselves, including the flagship terminals in Miami and Orlando, were designed as integrated multimodal hubs. Structural systems utilized long-span steel framing, while architectural cladding included aluminum composite panels, unitized glass curtain walls, and impact-resistant fenestration. Each station featured elevated platforms to streamline boarding, high-capacity vertical circulation elements, and advanced passenger information systems. Subgrade mechanical spaces housed electrical switchgear, HVAC chillers, and water reuse systems, all connected to centralized building management controls. Rolling stock was procured with an emphasis on energy efficiency, aerodynamic performance, and crash energy management. The train sets featured articulated cars with distributed traction motors, regenerative braking systems, and pressure-sealed cabins. Maintenance facilities along the corridor were equipped with drop pits, wheel lathes, and overhead cranes to support long-term fleet servicing. Throughout construction, scheduling and logistics were as crucial as engineering. Major portions of the corridor were built in active freight environments, requiring overnight possessions and strict coordination with existing operators. In urban areas, construction teams employed traffic diversion plans, temporary decking systems, and vibration monitoring to mitigate disruption to surrounding infrastructure. Environmental compliance was maintained through erosion control plans, wildlife monitoring programs, and wetland mitigation strategies. Ultimately, the completion of the Brightline Miami-Orlando high-speed rail line stands as a testament to integrated transportation engineering, blending high-performance rail systems with modern construction methodologies. The project not only introduces a new mode of inner-city travel, but also sets a precedent for how private investment and infrastructure innovation can reshape mobility across regional scales. The Giga Texas expansion, taking place at Tesla's sprawling manufacturing campus near Austin, Texas, represents a significant scaling effort aimed at boosting production capacity across multiple vehicle lines, battery systems, and structural components. Originally developed as a massive integrated factory for Model Y and Cybertruck production, the expansion adds several million square feet of manufacturing space, auxiliary facilities, and infrastructure to accommodate increased throughput and new production technologies. Construction activities began with clearing and earthworks on adjacent parcels of land to the existing plant, involving extensive excavation, grading, and soil stabilization to create uniform building pads capable of supporting heavy industrial structures. To counter the region's expansive clay soils, foundation work employed deep-drilled piers and reinforced concrete mat slabs. In some areas, ground improvement measures such as lime stabilization and geotextile reinforcement were used to enhance load-bearing capacity and mitigate settlement risks. The structural steel framework for the new buildings was erected using high-capacity cranes and modular assembly techniques to expedite construction timelines. Prefabricated steel columns, beams, and joists were bolted and welded into place, forming large-span bays that allow for uninterrupted production floor layouts. Roof systems were installed using insulated metal panels or single-ply membrane systems, supported by lightweight purlins and designed to accommodate mechanical units, skylights, and solar arrays. Interior construction followed a just-in-time approach, with mechanical, electrical, and plumbing trades coordinating installations to align with equipment delivery schedules. High-voltage electrical rooms, compressed air systems, process cooling loops, and ventilation ducts were integrated alongside the structural envelope. Specialized utility trenches were installed throughout the production halls to support robotic assembly lines, material handling conveyors, and automated guided vehicle systems. Battery production areas were fitted with climate-controlled environments, explosion-proof fixtures, and dry rooms with dehumidification systems to meet strict environmental controls required for lithium-ion cell manufacturing. These spaces required isolated foundations and vibration-damping floor assemblies to support precision machinery for electrode coating, cell assembly, and electrolyte filling. Additional facilities constructed as part of the expansion include logistics hubs, employee amenities, research labs, and test tracks. Roadways, stormwater detention ponds, and utility corridors were extended to support the new buildings, with site-wide infrastructure upgraded to handle the increased power demand and data connectivity. The expansion also incorporated sustainability elements such as rainwater harvesting, rooftop solar integration, and energy-efficient lighting systems. Once fully operational, the Giga Texas expansion will elevate the site's role as a central node in Tesla's manufacturing network, significantly increasing output across vehicle, battery, and structural component lines, while embedding advanced automation and vertically integrated production strategies into the facility's growing footprint. The O'Hare 21 Terminal expansion is a transformative infrastructure initiative designed to reconfigure and modernize one of the busiest airports in the world, Chicago O'Hare International. This project includes the expansion of Terminal 5, the demolition and complete replacement of Terminal 2, and the construction of 2 new satellite concourses that will be connected via underground pedestrian tunnels. The goal is to increase gate capacity, enhance passenger experience, and integrate international and domestic operations more seamlessly through what will be called the O'Hare Global Terminal. The process began with the expansion of Terminal 5, where the terminal was extended westward to add over 10 new gates. The expansion required major structural modifications, including deep foundation work using drilled shafts to support new concourse areas and jet bridges. Steel framing was erected in phased segments, coordinated tightly with ongoing airport operations to prevent disruption. Precast concrete panels, curtain wall systems, and advanced HVAC installations were used to ensure energy efficiency and expedited construction. Parallel to this, extensive enabling work was initiated for the new terminal core. This involved utility relocation, demolition of old utility tunnels, and excavation for new underground infrastructure. The most logistically demanding component is the future global terminal, which will replace Terminal 2. This new terminal will be built over active airfield areas, requiring a complex system of temporary taxiway realignments, structural decking over existing utilities, and phased demolition strategies to maintain uninterrupted air traffic operations. 2 new satellite concourses are being constructed west of the existing terminals. These concourses require pile-supported foundations due to the poor soil conditions and high groundwater table common to the site. Tunneling operations are underway to connect the new satellites with the main terminal. These tunnels are being bored using pressurized tunnel boring machines that install precast segmental linings as they advance, maintaining ground stability and controlling settlement risk near active runways. Each new terminal and concourse includes integrated baggage handling systems, advanced security screening infrastructure, and provisions for automated people mover expansions. Electrical systems are built with redundant power feeds, backup generators, and modern fire protection systems. The roofing structures are designed with large-span steel trusses to create open, column-free interior spaces, which are then fitted with custom architectural finishes reflecting local cultural themes. Throughout all phases, construction scheduling is meticulously planned using building information modeling and 4D sequencing to coordinate trades, manage passenger flow, and align with federal aviation security protocols. This expansion will not only increase the airport's capacity, but also completely redefine its functionality and resilience. At the heart of a massive urban revitalization effort, the Willets Point Soccer Stadium project emerges not only as a sports venue, but as a key piece of a complex redevelopment puzzle. Constructing a state-of-the-art stadium on a site formerly known for auto repair shops and contaminated soils involves far more than vertical construction. The first challenge is transforming the ground itself into a buildable foundation. a process requiring rigorous environmental remediation and extensive geotechnical preparation. Before any structural work begins, the site undergoes excavation of contaminated fill material, which includes petroleum-impacted soil and debris. Specialized crews follow a strict chain of custody protocol for soil sampling, segregation, and disposal. Remediation often involves the removal of several feet of surface material, followed by the installation of engineered fill and geotextile layers to cap and isolate any remaining residual contaminants. Groundwater treatment systems may also be installed to intercept and treat subsurface flow if hydrocarbon plumes are detected. Stadium construction begins with deep foundations, which are essential due to the site's prior use and potentially unstable subsurface conditions. A combination of drilled shafts and auger cast piles are used, designed to transfer loads through weaker upper strata into competent soil or rock layers well below grade. These piles are tested with static and dynamic load tests to confirm bearing capacity before concrete pile caps and grade beams are formed to create the structural base. The superstructure consists of a structural steel frame, prefabricated in sections off-site and trucked in for assembly using heavy lift cranes. Each piece is set into position using bolted connections and moment frames, forming a rigid skeleton for the seating bowl and roof structure. The stadium bowl is composed of precast concrete risers supported by steel raker beams, allowing rapid installation while ensuring consistency in alignment and dimensions. Vomitories, stair towers, and elevator cores are cast in place using high-strength concrete, reinforced with rebar cages tied and inspected on site. Roof systems vary by design, but for a stadium in this urban context, lightweight cantilevered trusses often support ETFE panels or metal decking to provide coverage without excessive shadowing or bulk. The cantilevers require counterweights or tension cables anchored deep into the structure to manage wind loads and uplift. Drainage systems are integrated into the roofing and seating areas to divert stormwater into underground retention systems, complying with city runoff regulations. Interior spaces such as locker rooms, concession areas, and mechanical rooms are built out once the primary structure is weather-tight. MEP systems are installed in coordination with architectural finishes, with central plant systems located in below-grade spaces or adjacent utility buildings. Electrical distribution includes robust conduit networks for lighting, broadcast infrastructure, and stadium-wide Wi-Fi systems. The playing field itself is constructed with precision grading and layered subsurface drainage. A sand-based root zone supports natural grass or hybrid turf, depending on the final performance criteria. Subsurface heating and irrigation systems are installed beneath the field surface, connected to central control units to maintain optimal playing conditions year-round. Completing the stadium includes extensive public realm improvements, sidewalks, plazas, lighting, and transit integration, transforming what was once industrial backland into a civic gathering place built to host tens of thousands of fans in a structure defined by engineering discipline and urban transformation. Perched high above the Colorado River, the construction of the Mike O'Callahan-Pat Tillman Memorial Bridge required a level of structural precision and environmental coordination seldom encountered in highway infrastructure projects. Spanning nearly 900 feet across the Black Canyon, just downstream of the Hoover Dam, the project's location presented formidable challenges, including extreme elevation, rugged topography, high winds, and protected surroundings. The goal was to reroute U.S. Route 93 traffic off the Hoover Dam, necessitating a bypass bridge that could support heavy truckloads while enduring significant thermal and seismic forces. Foundation work began with the construction of vertical columns anchored into the canyon walls. These columns required deep rock sockets drilled into the solid bedrock on both the Nevada and Arizona sides. Blasting, rock bolting, and controlled excavation were used to establish working platforms and construct reinforced concrete footings. Once the columns were complete, temporary cable stays were strung across the canyon to support the next phase, the twin-rib concrete arch that would ultimately carry the bridge deck. This twin arch was built using a cantilever segmental method. Crews cast concrete segments outward from each canyon wall in balanced pairs, inching their way across the gap with the aid of a cable-supported highline system and traveling formwork. As each segment cured, post-tensioning tendons were tensioned internally to bind the structure and prevent shear or flexural failure. Each section was surveyed and adjusted using hydraulic jacks to maintain precise alignment as the arch legs advanced toward mid-span. Upon closure of the arch, deck construction commenced. Steel girders were lifted by cranes stationed on temporary towers and connected to the arch ribs through vertical spandrel columns. The bridge deck itself was a cast-in-place concrete slab, poured in sections with embedded rebar and expansion joints to accommodate thermal movement. Barrier rails, lighting systems, and crash protection were then installed along the deck edges. Wind and seismic design were paramount. The bridge incorporates tuned mass dampers and elastomeric bearings at key support points, allowing it to flex under dynamic loading without structural compromise. To ensure safety during construction, catwalks and harness points were anchored throughout the span, and workers operated under a highly regimented fall protection protocol.
When construction commenced on the X-Energy and Dow Small Modular Reactor Nuclear Plant in Seadrift, Texas, it marked the integration of advanced nuclear technology within a chemical manufacturing complex. The site selection process prioritized co-location with industrial thermal demand, as the SMR units were designed not only to generate electricity, but also to provide high-temperature steam for Dow's process operations. The initial site preparation involved clearing and grading a large area adjacent to existing infrastructure, with heavy emphasis on creating a stable platform free of differential settlement risks. Soil stabilization was performed using lime treatment, and deep foundation work began with auger cast piles to support critical structures, including reactor containment buildings and turbine halls. The nuclear island construction required a precision-driven sequence of activities. Reinforced concrete foundations were laid for each reactor module, incorporating dense rebar mats and embed plates to support seismic resistance and load transfer. The containment vessel for each SMR unit was fabricated off-site and delivered in modular sections. These modules were lifted into place using heavy lift cranes and positioned within a below-grade reactor cavity formed by cast-in-place concrete with multi-layer waterproofing and radiation shielding components. Each containment structure included integrated penetrations for coolant loop connections, sensor conduits, and control rod drives. Structural liners were welded internally to provide a leak-tight barrier, while the reactor core itself, pre-assembled off-site, was lowered into the containment chamber using precision gantry systems. The high-temperature gas-cooled reactors employed TRISO fuel particles encased in graphite, requiring specialized fuel handling and containment systems that were installed within the fuel building adjacent to the reactor vault. Above ground, mechanical and electrical auxiliaries were housed in turbine generator halls and heat exchanger enclosures. Power conversion was managed using helium-to-water heat exchangers that fed steam turbines, with the secondary loop connecting to both electrical generators and steam distribution systems used within the Dow chemical complex. To support redundancy and reliability, multiple trains of pumps, valves, and isolation systems were installed with segregated routing to prevent common cause failures. Electrical infrastructure included switchyards and medium voltage transformers tied into the local grid, as well as on-site power distribution to serve critical process loads. Instrumentation and control systems were centralized in a seismically isolated control building, equipped with safety-class digital control systems capable of autonomous reactor shutdown and passive cooling initiation. Fiber optic communication networks linked every module to this control hub for real-time data monitoring and diagnostics. Cooling systems relied on both mechanical draft cooling towers and auxiliary dry cooling radiators, designed to operate under varying ambient conditions while minimizing water withdrawal from nearby sources. Construction crews also installed extensive underground piping networks for the primary and secondary coolant loops, each pressure tested and radiographically inspected to meet nuclear-grade quality assurance standards. To ensure regulatory compliance, all phases of the project were conducted under a rigorous quality assurance framework, with continuous inspection and documentation in accordance with Nuclear Regulatory Commission requirements. Once systems were installed, integrated commissioning followed a phased approach, beginning with cold testing and followed by hot functional testing using non-nuclear heat sources. Only after successful completion of all operational verifications was fuel loading authorized. Upon activation, the SMR units began delivering reliable, carbon-free energy and industrial-grade steam, establishing the facility as a pioneering model for hybrid energy production in industrial settings.
The Golden Triangle Polymers project is a significant petrochemical development located in Orange County, Texas, designed to produce polyethylene from ethane feedstock derived from natural gas. This multi-billion-dollar facility includes a world-scale ethane steam cracker and several polyethylene production units, intended to supply high-performance plastic resins for global markets. The project's name is derived from the local region known as the Golden Triangle, a historically industrialized area defined by the cities of Beaumont, Port Arthur, and Orange. Construction of this complex involves massive civil, structural, mechanical, and electrical works, integrating advanced process technologies with robust environmental and safety systems. Site development commenced with bulk earthworks, where tens of thousands of cubic yards of soil were excavated, compacted, and leveled. Ground improvement techniques such as surcharge preloading and deep soil mixing were employed to mitigate settlement risks due to the area's soft, compressible soils and high water table. A dense network of underground utilities, including stormwater drainage, fire water lines, and chemical-resistant process sewers, was installed beneath reinforced concrete foundations that support the heavy process equipment. The ethane cracker, the core of the facility, operates by heating ethane to over 1,500 degrees Fahrenheit in large cracking furnaces. These furnaces were assembled on deep foundations and equipped with radiant coils and convection sections fabricated from high-temperature alloys. The cracked gas is then rapidly quenched to halt the reaction, routed through a series of compressors, and subjected to cryogenic separation processes to isolate ethylene from other hydrocarbons. This required the construction of tall distillation towers, complex heat integration systems, and high-pressure ethylene pipelines, all of which demanded exacting tolerances and strict adherence to process safety protocols. The polyethylene units downstream involve polymerization reactors, pelletizers, and storage silos. Each unit required precise mechanical installation, including the alignment of extruders and gear pumps, supported by large structural steel frameworks and enclosed in metal-clad buildings with integrated ventilation and dust collection systems. Electrical works included high-voltage substations, cable tray networks spanning miles, and process automation systems featuring thousands of field instruments connected to a centralized distributed control system. Construction logistics were coordinated through modularization strategies, with prefabricated pipe racks, equipment skids, and control rooms transported to the site and lifted into position using heavy lift cranes. The facility also features a dedicated rail and truck loading infrastructure for product distribution. Upon completion, the Golden Triangle Polymers project will reinforce the region's standing as a global center for chemical manufacturing, leveraging abundant natural gas resources and state-of-the-art engineering to produce essential plastic materials. Waterline Tower is a super-tall mixed-use skyscraper under construction in Austin, Texas, set to become the tallest building in the state upon completion. Rising over 1,000 feet, it is engineered to combine residential, office, hotel, and retail functions within a single vertical structure, making it one of the most complex high-rise builds in the region. The tower's footprint is situated adjacent to Lady Bird Lake, requiring careful geotechnical planning and foundation engineering due to its proximity to the water and variable subsurface conditions. The construction process began with site clearing, excavation, and the installation of deep foundations. Because of the tower's extreme height and slender profile, engineers opted for a mat foundation supported by drilled piers. These piers are bored hundreds of feet into stable bedrock, reinforced with high-strength steel rebar cages and filled with tremmy concrete. The mat slab above them is a multi-foot thick concrete platform designed to distribute the tower's vertical loads evenly across the pier array. Following foundation work, vertical construction commenced with the use of a high-capacity jump form system to cast the central concrete core. This core houses elevators, stairwells, mechanical shafts, and acts as the primary structural spine resisting lateral loads such as wind and seismic forces. The concrete used in the core is high strength, often exceeding 10,000 psi, and is poured in successive lifts to maintain structural continuity and construction pace. Around the core, a steel and concrete floor framing system is constructed floor by floor. Composite steel beams span outward from the core to perimeter columns, supporting metal decking over which lightweight concrete slabs are poured. Post-tensioning is employed in certain areas to reduce slab thickness while maintaining structural performance. Construction cranes anchored within the building's core assist with vertical material transport and are periodically climbed upward as the tower rises. The facade is composed of a high-performance curtain wall system with floor-to-ceiling glass, aluminum mullions, and integrated sun shading features. The curtain wall panels are pre-assembled and hoisted into place to accelerate enclosure and allow interior fit-out to begin on lower floors, while upper levels are still being built. Mechanical floors, typically located at intervals, house equipment such as HVAC chillers, pumps, electrical switchgear, and water tanks. These are acoustically and structurally isolated to minimize vibration and noise transfer to tenant spaces. The top of the tower includes tuned mass dampers and structural outriggers that tie the core to perimeter columns, increasing lateral stiffness. Overall, Waterline Tower represents an intricate orchestration of advanced engineering, material logistics, and construction management, executed under tight spatial constraints and ambitious scheduling within an active urban environment. Constructing an academic building in the dense urban fabric of Manhattan presents challenges distinct from traditional campus development. The new academic building for the Fashion Institute of Technology had to reconcile limited lot dimensions, adjacent high-rise structures, and continual campus operations with the technical ambition of a vertically organized, highly specialized educational facility. From excavation to final systems commissioning, each stage of construction required precision scheduling, structural creativity, and adaptive coordination among trades. Foundation work commenced with site excavation, bounded by existing college buildings and street infrastructure. Due to space constraints, materials handling was tightly regulated with just-in-time delivery protocols and vertical staging. The site was prepared with soldier pile and lagging retaining walls to stabilize the excavation before the deep foundations were installed. Given Manhattan's bedrock proximity, drilled shafts socketed into schist or spread footings on rock were employed, depending on the structural loading zones. The superstructure was framed using a reinforced concrete core combined with a structural steel skeleton, an approach balancing rigidity with floor plan flexibility. The core housed vertical circulation, bathrooms, and utility risers, cast in sequence to maintain construction momentum. The steel framing proceeded floor by floor, using mobile tower cranes erected within tight street setbacks. Fireproofing crews followed closely behind steel erection, applying spray-on materials in coordination with weather protection and enclosure installation. The building envelope emphasized energy performance and natural daylighting, incorporating high-performance curtain wall systems. These facades featured insulated glazing with low emissivity coatings, aluminum mullions with thermal breaks, and integrated solar shading elements. The installation of the curtain wall followed a sequential glazing process using swing stages and exterior lifts. Connections between the curtain wall and concrete slabs included thermal isolation pads and expansion joints to account for building movement and thermal cycling. Inside, the layout accommodated specialized spaces such as design studios, lecture halls, fabrication labs, and exhibition areas. Floor structures were reinforced and acoustically isolated in zones requiring heavy equipment or high sound attenuation. Interior partitions used cold-formed metal framing and high-density gypsum board, often layered with acoustic insulation or resilient channels in areas adjacent to classrooms or performance spaces. Mechanical, electrical, and plumbing systems were designed with adaptability and energy conservation in mind. Air handling units were located on mechanical floors and rooftop penthouses, serving variable air volume zones controlled by digital building management systems. Exposed ductwork in select areas supported the industrial aesthetic of design education environments while maintaining accessibility for maintenance. Hydronic heating and chilled water loops were integrated into the slab structure in certain areas, supporting radiant temperature control. Lighting design utilized daylight-responsive LED fixtures networked into a centralized control system. Occupancy sensors, dimming controls, and programmable lighting scenes provided both energy efficiency and flexible ambiance suited for different academic tasks. Electrical panels and communication rooms were distributed vertically in stacked risers, with horizontal branch wiring routed through raised floors or suspended trays to simplify future reconfiguration. Final commissioning included HVAC balancing, system testing, emergency power simulation, and fire alarm integration. With its vertical organization, modern utility core, and adaptive lab spaces, the FIT academic building reflects a technically intricate approach to education infrastructure, delivering high-performance functionality within the vertical constraints of its Manhattan environment. One of the most logistically demanding elements of the Las Vegas Convention Center expansion was its integration with an active facility that could not afford operational downtime. The construction team had to carefully phase demolition, excavation, and vertical build-out around major events and conventions, often working night shifts and off hours to avoid disruptions. The expansion project added more than 1 million square feet of new space, including exhibit halls, meeting rooms, and circulation areas, requiring a steel and concrete structural system capable of spanning large, column-free zones. The foundation work began with deep excavation and pile driving. Given the loose alluvial soils common in the Las Vegas Valley, crews installed hundreds of auger-cast piles, each reinforced with steel cages and tremie-poured concrete. A thick mat slab was then poured over this foundation grid, embedded with conduits for electrical distribution and floor drainage systems. The use of high-strength concrete mixes with specific slump tolerances ensured uniform performance and reduced cracking across the massive floor plate. The superstructure utilized a composite framing system combining wide-flange steel beams and concrete floor decks cast over metal decking. This method provided both strength and speed, allowing trades to follow closely behind the steel erection teams. Tower cranes and mobile telescopic cranes hoisted beam segments and roof trusses into place. For the convention hall roofs, long-span trusses were assembled in staging yards and lifted in modular sections to minimize on-site welding and alignment complexity. Mechanical, electrical, and plumbing systems were designed with scalability and adaptability in mind. Overhead utility zones carried air handling units, fire suppression mains, and lighting circuits along open web joists. These zones were isolated for sound attenuation, using acoustic baffles and vibration isolators to prevent mechanical noise from disrupting presentations and exhibits. Air distribution was handled through a combination of high-volume diffusers and underfloor displacement systems, ensuring comfort across densely populated exhibit spaces. The facade was clad in curtain wall glazing, aluminum composite panels, and architectural fins designed to reduce solar heat gain while delivering a visually striking presence along the strip. Exterior systems were tested for wind and water penetration using mock-up assemblies before full-scale deployment. The entire expansion was tied into a building automation system, enabling real-time monitoring of energy use, HVAC status, and life safety systems across both new and existing facilities.
Initial groundwork for Phase 1 of the Texas LNG export terminal in Brownsville began with intensive marine and geotechnical surveys to assess the suitability of the shoreline for deepwater infrastructure. The construction site required extensive dredging operations to create a navigable ship channel and turning basin capable of accommodating LNG carriers. Cutter suction dredgers and hopper dredgers were deployed to remove millions of cubic yards of sediment, which were relocated to designated containment areas built with sheet pile enclosures and geotextile reinforcement. Onshore, the site was cleared and leveled using heavy earth-moving equipment, with special attention paid to creating stable embankments for heavy process equipment. Piling operations commenced early, with cast-in-place concrete piles driven deep into coastal clay strata to support both structural and mechanical loads. Foundation pads for the liquefaction trains, storage tanks, and auxiliary buildings were constructed using a combination of deep pile caps and heavily reinforced grade beams. The heart of the terminal, the liquefaction process units, were installed on elevated steel platforms designed to withstand hurricane-force winds and seismic events. Each train included gas pretreatment modules, cryogenic heat exchangers, and compressor skids that were prefabricated off-site and delivered via heavy haul transport. The refrigerant circuits used a combination of propane and mixed refrigerants, requiring precise installation of high alloy piping systems and high-capacity centrifugal compressors. Storage infrastructure featured full containment LNG tanks built with a pre-stressed concrete outer wall and a nickel alloy inner tank. These tanks were founded on deep mat slabs and included a suspended deck for boil-off gas handling equipment. Tank construction followed a sequential slip-forming technique for the concrete shell, while cryogenic insulation and inner tank welding were performed under tightly controlled environmental conditions. Loading infrastructure was built at the end of a new trestle-supported marine jetty. The jetty deck housed cryogenic piping, loading arms, vapor return lines, and safety systems, all supported by battered steel piles driven into the seafloor. The loading arms were installed with emergency release systems and swivel joints to accommodate tidal variation and vessel movement. Throughout the terminal, fire protection systems were deployed with high-volume deluge systems, gas detection arrays, and foam monitors at critical points. Instrumentation and control were integrated into a distributed control system housed within a blast-resistant operations center. By the end of Phase 1, the Texas LNG export terminal was equipped to handle its first liquefaction and loading operations, forming a cornerstone of U.S. Gulf Coast LNG export capacity.
The Northern Corridor roadway projects in Frisco, Texas, represent a comprehensive infrastructure initiative aimed at accommodating the city's rapid growth and enhancing transportation efficiency. With an investment exceeding $200 million, the city is undertaking 10 major roadway construction and improvement projects, encompassing over 65 miles of new and upgraded roadways. These projects are strategically distributed throughout the Northern Corridor, particularly within the expansive Fields development, a 2,500-acre master-planned community. Construction activities began with extensive site preparation, including land clearing, grading, and the installation of erosion control measures to stabilize the terrain. Subsurface investigations were conducted to assess soil conditions, informing the design of robust foundation systems capable of supporting the anticipated traffic loads. Utility relocation efforts were coordinated to ensure uninterrupted services during the construction phases. Key projects include the widening and extension of Panther Creek Parkway, transforming it into a 6-lane divided roadway to improve east-west connectivity. This involved the construction of new pavement sections, stormwater drainage systems, and the installation of traffic signals at major intersections. Similarly, The expansion of Legacy Drive and Fields Parkway required the reconstruction of existing roadways, incorporating additional lanes, medians, and pedestrian pathways to enhance safety and capacity. The Dallas North Tollway is undergoing significant reconstruction, with more than 18 miles of main lanes being widened to accommodate increasing traffic volumes. This complex operation necessitated the use of advanced construction techniques, such as phased construction to maintain traffic flow, the deployment of high-capacity cranes for bridge beam placements, and the implementation of intelligent transportation systems for real-time traffic management. Frisco Street North is being developed as a new two-lane roadway connecting Universal Parkway to PGA Parkway. This project includes the construction of a new roadway base, asphalt paving, and the integration of signage and lighting systems to meet modern roadway standards. The design also incorporates provisions for future expansion, anticipating continued growth in the area. Throughout the corridor, attention is given to multimodal transportation options. Sidewalks, bike lanes, and shared-use paths are being integrated into the roadway designs, promoting alternative modes of transportation and enhancing community connectivity. Landscaping efforts, including the planting of native vegetation and the installation of irrigation systems, are also underway to improve the aesthetic appeal of the corridors. The Harbor Bridge project in Corpus Christi, Texas, is an extensive civil engineering effort focused on replacing the original through-arch bridge built in the mid-20th century with a modern, cable-stayed structure designed to meet 21st century transportation demands and navigational standards. The new bridge is engineered to span the Corpus Christi Ship Channel, allowing for increased clearance to accommodate larger cargo vessels entering the port of Corpus Christi while also expanding traffic capacity for roadway users. Construction began with the extensive groundwork necessary to support such a large-scale bridge. This included site clearing, utility relocations, and the construction of temporary access roads and work trestles. Deep foundation work was performed for the main towers, which support the cable-stayed spans. These foundations consisted of drilled shafts extending hundreds of feet into the soil and rock layers below, designed to support the enormous vertical and horizontal loads transmitted from the bridge deck through the cables and into the towers. The main span is being built using the balanced cantilever construction method. Precast concrete segments are fabricated off-site in a dedicated casting yard. Each segment is trucked to the site, lifted into place using specialized cranes or launching gantries, and then secured using high-strength epoxy and post-tensioning tendons. This method allows segments to be added symmetrically from each side of the tower, maintaining equilibrium and reducing the need for temporary supports in the shipping channel. The bridge's superstructure includes two massive pylon towers, constructed using slip-form techniques that allow continuous vertical casting of concrete. These towers rise to over 500 feet above the channel and anchor the array of stay cables that fan out diagonally to hold the deck in place. Each cable consists of multiple high-tensile steel strands, sheathed in protective coverings to resist corrosion in the coastal environment. On either side of the main span, long elevated approach viaducts are being constructed. These consist of precast or cast-in-place concrete girders supported on piers, which in turn rest on pile foundations. Road deck construction includes forming and pouring concrete slabs, installing parapets, expansion joints, drainage systems, and integrating lighting, traffic sensors, and barrier systems. When completed, the new Harbor Bridge will not only be an architectural landmark, but also a critical freight and commuter route engineered to last for over a century under dynamic traffic and environmental conditions. Beneath the dense urban landscape of the northeastern United States, the Gateway Program's Hudson River Tunnel project emerges as one of the most intricate and vital rail infrastructure undertakings in the country. At its core, the tunnel is designed to bolster the heavily trafficked Northeast Corridor by constructing new twin tunnels beneath the Hudson River, providing a long overdue supplement to the existing pair of century-old tunnels that currently operate at near full capacity. Construction begins with extensive geotechnical investigations to map out the subsurface conditions beneath both the river and the surrounding urban areas. This involves drilling boreholes, performing seismic refraction surveys, and collecting core samples to evaluate the composition and stability of the underlying rock and sediment. Because the Hudson River bed consists largely of soft silt and clay atop layers of glacial till and bedrock, tunnel boring machines must be selected and calibrated with these highly variable ground conditions in mind. Launching the tunnel drives requires the excavation of deep approach shafts on both the New Jersey and Manhattan sides. These shafts provide access for tunnel boring machines and serve as critical logistical hubs for removing excavated material and bringing in precast concrete segments. Due to spatial constraints, particularly on the Manhattan side, where active rail lines and dense development restrict movement, all construction staging and materials delivery must be meticulously coordinated to avoid disruptions to existing rail operations. Tunnel boring machines used in this project are earth pressure balance types, capable of maintaining face stability while simultaneously installing the tunnel lining. These machines advance gradually, segment by segment, using a rotating cutter head to excavate material, while hydraulically driven erector arms install curved precast concrete segments into a ring formation. These segments are tightly bolted and gasketed to form a watertight structure capable of resisting the intense pressures from both the river and surrounding soil. As the tunnel progresses beneath the river, constant monitoring systems are deployed to detect ground settlement, machine performance, and water ingress. These systems ensure that any anomaly is detected and mitigated before it can threaten the structural integrity of the tunnel or impact above-ground infrastructure. Ventilation and safety systems are gradually installed behind the boring machines, including emergency egress pathways, fire suppression conduits, and future cabling ducts for power and communications. Upon completion of boring, the tunnel interiors must be outfitted with track systems, traction power supply, signaling equipment, and drainage systems. Specialized crews install continuous welded rail on concrete ties, ensuring smooth and safe high-speed travel. The power infrastructure includes overhead catenary lines supported by rigid cantilever arms, interfaced with substations to provide consistent electrical feed to passing trains. Advanced signal systems, designed for positive train control integration, are installed to meet current federal safety standards and accommodate future automation capabilities. When a bridge reaches the end of its useful life, replacement becomes not just a matter of modernization, but of safety and resilience. This principle guided the reconstruction of the Tioughnioga River Replacement Bridge, a project set in motion to restore reliable vehicular connectivity across the river while improving structural standards and accommodating future load demands. The existing bridge, after decades of service, exhibited wear typical of aging steel and concrete structures exposed to freeze-thaw cycles, road salt, and high water events. In the vast and rugged terrain of western Nevada, the Greenlink West Transmission Line project began with a series of extensive environmental and geotechnical surveys. This corridor, stretching hundreds of miles, demanded careful route selection to avoid sensitive habitats, archaeological sites, and unstable soil zones. Once the alignment was finalized, crews mobilized with access road grading as the first priority. In remote desert areas, temporary haul roads and helicopter pads were established to enable movement of personnel, equipment, and materials to tower sites that had no existing access. Tower foundations varied depending on soil conditions. In rocky upland zones, foundation crews used blast hole drilling, followed by concrete anchors set deep into fractured bedrock. In softer or sandy valley floors, deep bored shaft foundations were poured with reinforced concrete, sometimes with steel casing to prevent wall collapse. Each foundation was designed to handle both axial and lateral loads imposed by conductor tension and wind shear on the towers. Concrete had to be batched locally or transported in rotating mixers across significant distances, requiring careful coordination to ensure consistency and curing integrity. The transmission towers themselves were largely lattice steel structures, fabricated off-site and delivered in sectional bundles. Erection crews used tracked cranes where terrain allowed, while in the steepest sections, helicopters were employed to lift tower segments into place. Ground crews then bolted the segments together using high-strength structural fasteners. Each tower was surveyed post-erection for verticality and alignment using laser theodolites before conductor stringing began. Conductor installation involved multiple phases. First, pilot lines were pulled between towers using drones or helicopters. These were then used to draw in heavier steel messenger cables, which in turn pulled in the high-voltage conductor bundles. Each conductor was tensioned using hydraulic pullers and tensioners to exact sag tolerances specified in the design documents. Spacer dampers were installed at calculated intervals to prevent aeolian vibration, and insulators, often made from composite polymer materials, were mounted to separate the live conductors from the grounded towers. Substations on either end of the line required massive transformers, circuit breakers, and control systems to manage voltage conversion and grid integration. These substations were built concurrently, with site grading, pad installation, and bus work assembly proceeding, while the main line was being erected. The Greenlink West project not only involved transmission infrastructure, but also included communications fiber installation and SCADA integration for remote monitoring, forming a backbone for a more resilient and renewable-focused power grid across the region.
Launching the Austin-Bergstrom International Airport expansion required a meticulously phased approach to integrate new facilities without disrupting ongoing operations. The initial stages focused on enabling works, including rerouting of utilities, relocation of existing service roads, and reinforcement of airside security perimeters. Survey crews used LiDAR and ground-penetrating radar to map existing underground infrastructure and coordinate precise tie-ins with the new systems. Temporary construction access points were established, and logistic staging areas were demarcated to accommodate a steady flow of materials, heavy equipment, and prefabricated assemblies. Foundation work for the new terminal sections, concourses, and utility buildings involved deep excavation and concrete piling. Soil conditions near the former military airbase zones necessitated dynamic compaction in some sectors to stabilize the subgrade. Once load-bearing conditions were confirmed, pile caps and grade beams were poured using high-performance concrete. Reinforcement detailing was designed to account for seismic, wind, and thermal stresses typical of large-span airport structures. The superstructure utilized a combination of structural steel framing and long-span trusses to create open interior volumes for the new concourses. Prefabricated steel components were erected using crawler cranes with sequential bolting patterns and diagonal bracing to maintain geometric alignment. Above the passenger areas, a lightweight roof system integrated insulated metal panels and skylights to introduce natural light while meeting thermal and acoustic insulation standards set by FAA and LEED requirements. Interior slab-on-deck pours were coordinated with embedded conduit runs for electrical and data distribution. Elevated mechanical mezzanines were constructed to house air handling units, VAV boxes, and ductwork runs that supplied the expanded terminal zones. HVAC systems were zoned for redundancy and integrated into the airport's existing energy management system. The use of underfloor air distribution in certain gates improved thermal efficiency and passenger comfort. New baggage handling systems were implemented beneath the terminal deck, including high-speed conveyor belts, RFID tagging stations, and inline explosives detection machines. These systems were supported by structural trenches and service catwalks, allowing maintenance crews full access during operations. The installation followed a phased commissioning schedule to maintain the functionality of existing carousels while integrating the new loops. Airside expansion included the extension of taxiways and aircraft apron areas, using Portland cement concrete pavement with deep dowel baskets and expansion joints designed for wide-body aircraft loads. Precision laser grading ensured consistent pavement elevation, and pavement marking was performed with high reflectivity thermoplastics for visibility in adverse weather. jet bridges, and ground support infrastructure were pre-installed on apron pads before gate commissioning. The new concourses were fitted with advanced security screening areas, including automated tray return systems and computed tomography scanners for carry-on luggage. Passenger amenities such as lounges, concessions, and smart wayfinding kiosks were installed with integrated digital infrastructure. This required robust Wi-Fi, Bluetooth beacon arrays, and digital signage mounted throughout the terminal core and satellite areas. To close out the expansion, life safety systems, including fire alarms, emergency lighting, and evacuation audio, were tested under full operational loads. Airport staff underwent simulation-based training in the new spaces, while system-wide performance tests validated HVAC loads, electrical grid balancing, and communications interoperability. With the completion of the expansion, Austin Bergstrom was equipped to handle future demand increases with improved passenger flow, aircraft accommodation, and operational resilience.
The Terminal B modernization project at George Bush Intercontinental Airport in Houston is a comprehensive reconstruction effort aimed at transforming one of the airport's oldest terminals into a modern facility that meets current and future demands for domestic regional air travel. The modernization spans structural, architectural, mechanical, and technological upgrades across both the north and south concourses, significantly enhancing passenger experience and operational efficiency. The project began with demolition activities focused on aging infrastructure, including removal of outdated gate structures, baggage systems, mechanical rooms, and interior finishes. Careful sequencing allowed active terminal operations to continue throughout construction, with temporary walls and rerouted passenger pathways maintaining secure access zones and minimizing disruptions. Heavy demolition equipment was mobilized during nighttime shifts to dismantle structural components, followed by hauling of debris off-site and preparation of new construction zones. New foundations were laid using reinforced concrete footings and grade beams supported by drilled piers to address the expansive clay soils common in the Houston area. Structural steel framing was erected to form the skeleton of the expanded concourses, designed to support taller ceilings and larger open-span interiors. Lateral stability was achieved using cross-bracing and moment frame assemblies, ensuring the building could withstand high wind loads typical of Gulf Coast storms. Architectural improvements included curtain wall systems with energy-efficient glazing, metal panel cladding, and expanded roof canopies. The terminal was outfitted with high-efficiency HVAC systems, LED lighting, and building automation systems integrated through a centralized control platform. Interior finishes were selected for durability and aesthetics, featuring terrazzo flooring, stainless steel accents, and acoustic ceilings to manage noise levels in busy passenger areas. Gate areas were redesigned to accommodate dual boarding bridges for regional jets and larger aircraft, with apron modifications including new fuel pits, storm drains, and aircraft service utilities. The baggage handling system was fully replaced with a high-speed, RFID-enabled conveyor network that streamlines sorting and routing. Mechanical rooms were upgraded with variable frequency drive pumps, chillers, and air handling units, sized to meet the demands of modern terminal operations. Passenger amenities such as expanded seating areas, charging stations, restrooms, concessions, and signage were all reimagined to provide a seamless and intuitive travel experience. Security screening areas were reconfigured to improve throughput and align with TSA's latest technology standards, incorporating automated bin return systems and integrated body scanners. Upon completion, the Terminal B modernization will significantly boost capacity for United Airlines and regional carriers, transforming the terminal into a state-of-the-art hub equipped to handle millions of passengers annually with increased comfort, efficiency, and architectural sophistication. The Frederick Douglass Tunnel is a major infrastructure endeavor designed to replace the Civil War-era B and P Tunnel in Baltimore, Maryland, a critical bottleneck along the Northeast Corridor. The new tunnel will increase capacity, improve reliability, and allow for higher speed travel for both passenger and freight rail. It involves the construction of 2 new parallel rail tunnels, each approximately 2 miles long, designed for electric Amtrak and MARC trains, while also preparing the corridor for potential future upgrades. The construction process begins with preparatory work, including land acquisition, environmental remediation, and utility relocation. Due to the urban setting, crews must identify and divert existing sewer, water, and communication lines that intersect the future tunnel alignment. Extensive geotechnical investigations are carried out along the alignment, using boreholes and geophysical instruments to map subsurface conditions. These findings inform the selection of tunnel boring machine technology and the design of support systems for the tunnel lining. The primary construction method involves using large tunnel boring machines to excavate through a mix of soil and rock beneath West Baltimore. Launch shafts are constructed at staging areas, requiring deep excavations supported by secant pile walls or slurry wall systems to maintain soil stability. Once the shafts are completed, the tunnel boring machines are assembled in segments and lowered into place. As each machine advances, it excavates material which is conveyed back to the surface, while simultaneously installing precast concrete tunnel segments to form the permanent lining. Above-ground structures include a new West Baltimore station, portal structures at either end of the tunnel, and ventilation shafts spaced strategically along the alignment. Each tunnel bore includes track slab construction, overhead catenary systems for electric traction, signal conduits, emergency walkways, and fire life safety systems. These elements are built sequentially following tunnel excavation, requiring multiple specialized crews operating in coordination. To handle stormwater and groundwater intrusion, sump pits and drainage systems are integrated along the tunnel invert, with pumping stations to discharge water safely. Tunnel ventilation systems include jet fans and shafts to manage air quality and smoke extraction in emergency scenarios. Substations are constructed nearby to deliver traction power, linked by high-voltage feeders running through dedicated conduit banks. Once both tunnel bores are completed and internal systems installed, track is laid and aligned to tight tolerances to support high-speed rail operations. Extensive systems testing follows, including power supply validation, signaling integration, and emergency response simulations. Upon completion, the Frederick Douglass Tunnel will replace a nearly century-and-a-half-old choke point with modern, resilient infrastructure capable of supporting the Northeast Corridor's next generation of rail travel. Revitalizing a historic waterfront facility for 21st century industrial and renewable energy needs, the South Brooklyn Marine Terminal presents a unique case study in urban maritime infrastructure development. Situated on the edge of New York Harbor, the terminal's redevelopment hinges on heavy structural upgrades, environmental remediation, and the integration of new logistics capabilities tailored to offshore wind, bulk cargo, and intermodal freight handling. The initial phase of transformation involves evaluating the structural condition of the existing waterfront bulkheads, piers, and yard surfaces. Many of these elements date back several decades and suffer from deterioration due to tidal action, saltwater corrosion, and lack of continuous maintenance. Engineers perform sonar surveys and underwater inspections to assess the condition of timber piles, concrete caps, and steel sheet piles. Based on these findings, repair or full replacement strategies are selected. In many areas, new sheet pile walls are driven, reinforced with tiebacks and anchor rods connected to landward deadmen buried beneath newly placed compacted fill. Yard space across the terminal is reconstructed with load-bearing capacity in mind. The goal is to accommodate heavy crawler cranes, nacelle transporters, and oversized offshore wind turbine components. Subgrade stabilization may include dynamic compaction or deep soil mixing to reinforce the ground, followed by layered gravel bases and heavy-duty concrete or asphalt paving systems. Drainage systems are upgraded in parallel to manage stormwater runoff and prevent pooling on wide open surfaces that span several acres. Maritime access upgrades include dredging the berth to maintain appropriate depth for deep draft vessels. Clamshell dredging techniques remove sediment under environmental oversight, with turbidity curtains deployed to minimize dispersion. Dredged materials are tested and either treated or transported to designated disposal or reuse sites. New fendering systems and mooring bollards are installed along the quay walls to support ships delivering wind turbine towers, blades, and monopiles. The redevelopment integrates electrical and data infrastructure into the terminal footprint, essential for handling modern logistics and power-intensive operations. High-capacity substations, switchgear, and underground conduit networks are installed to support lighting, crane operations, and refrigerated containers. Fiber optic cabling ensures real-time coordination of equipment and inventory, and integrated control systems allow remote monitoring of yard activity and vessel movements. To accommodate rail connectivity, existing track alignments are restored and upgraded with new ballast, ties, and signal systems, enabling seamless intermodal transfer between ship, truck, and rail. Rail spurs are aligned to serve warehousing and storage zones efficiently, reducing turnaround time for large or awkward cargo. Heavy lift pads and roll-on to roll-off ramps are constructed to handle self-propelled modular transporters and specialized trailers. Finally, the terminal is configured to serve as a staging hub for offshore wind development. This includes designated laydown areas for wind turbine components, reinforced assembly zones, and barge loading platforms. Specialized lifting equipment, such as pedestal cranes or self-erecting gantries, is permanently installed or brought in on a project basis. The combination of marine access, ground capacity, and logistics integration positions the South Brooklyn Marine Terminal as a cornerstone of regional industrial infrastructure, engineered to support both current freight needs and the future of clean energy deployment. Construction of the Brightline West high-speed rail begins not with rails, but with an extensive corridor preparation effort stretching along the Interstate 15 right-of-way between Southern California and Las Vegas. The alignment was selected to leverage existing transportation corridors, minimizing environmental impact while reducing the need for new land acquisition. Survey teams marked out the route using GPS-based geolocation, after which clearing and grubbing crews removed desert vegetation and leveled the alignment in preparation for subgrade construction. Due to varying soil conditions, crews implemented soil stabilization techniques such as cement treatment and moisture conditioning to achieve the compaction required for long-term settlement resistance. The rail substructure comprises several layers, beginning with compacted subgrade, followed by engineered fill, and a layer of ballast in zones where traditional track is used. However, in high-speed segments, especially those reaching over 180 miles per hour, a concrete slab track system will be utilized. This involves pouring continuous reinforced concrete slabs with expansion joints and embedded fasteners designed to hold the rail in place with millimeter-level precision. These slabs are set atop geotextile membranes and drainage systems to prevent water infiltration and thermal heave. Bridges and viaducts form a critical part of the project, particularly where the line crosses over existing roadways or environmentally sensitive terrain. Precast concrete girders are transported via specialized haulers and lifted using high-capacity gantry cranes. Abutments and piers are constructed using drilled shaft foundations, with rebar cages tied on site and lowered into the shafts before concrete placement. In seismic zones, isolators and energy-dissipating devices are installed to ensure structural resilience during earthquake events. Catenary systems for electric power delivery require the installation of overhead contact system, poles spaced at precise intervals along the corridor. These poles are anchored in concrete footings and support tensioned copper conductors delivering 25 kilovolts AC. Power substations are built at strategic intervals, converting utility-scale electricity to the necessary specifications for the trains and feeding the system through switchgear and protection circuits. Stations are designed as intermodal hubs, integrating ticketing systems, security screening, vertical circulation, and baggage handling. platform edge doors, vibration damping structural slabs, and acoustically treated canopies are incorporated to ensure comfort and safety at high-speed boarding conditions. All systems are tied into a centralized traffic control center that uses fiber optic networks and redundant data links for command, monitoring, and dispatch. Brightline West aims to redefine regional travel by delivering a fully electric, high-capacity corridor built with exacting civil and systems integration standards tailored for American infrastructure.
Breaking ground on the VIA Green Line bus rapid transit system required an initial phase of utility mapping and right-of-way coordination through densely developed urban corridors. The alignment followed major arterial roads, necessitating collaboration with city departments and utility companies to relocate existing infrastructure, including water mains, sewer lines, gas pipes, and fiber optic cables. Engineers conducted subsurface utility engineering surveys to precisely map underground features and avoid costly conflicts during construction. After right-of-way clearance, the corridor was milled and excavated in segments to prepare for the installation of the dedicated BRT lanes. Existing asphalt was removed, and the underlying subgrade was reshaped and compacted. Geotechnical stabilization methods were employed where soft soils threatened pavement integrity. These included cement or lime treatment of subgrade layers, especially in areas with expansive clay content common in the region. Base layers were constructed using crushed stone with geogrid reinforcement used at select locations to distribute vehicular loads and reduce differential settlement. Dedicated BRT lanes were then surfaced with high-strength asphalt mixes designed for the repetitive load cycles of rapid transit buses. These lanes were constructed with increased structural depth and improved cross-slope design to enhance drainage and longevity. Curbs and gutters were reformed to accommodate new lane configurations, and bioswales were integrated at strategic locations for stormwater management. Station construction was a major feature of the project. Each BRT station was built with elevated platforms to ensure level boarding, thereby enhancing accessibility and minimizing dwell times. Platforms were constructed using reinforced concrete pads and integrated with steel-framed canopies, which included solar panels for auxiliary power. Electrical conduits were laid beneath the platform surface to support lighting, real-time arrival displays, and fare payment systems. The installation of tactile warning strips and ADA-compliant ramps ensured full accessibility. Signal prioritization infrastructure was installed at major intersections. This involved retrofitting existing traffic signals with transit signal priority controllers that could receive real-time data from approaching BRT vehicles via GPS and cellular communications. Fiber optic backbone was extended along the corridor to provide connectivity for TSP, as well as for security cameras and station monitoring. To support fleet operations, bus-only lanes were demarcated with thermoplastic pavement markings and vertical delineators where necessary. Concrete barriers were used in some high-conflict zones to physically separate BRT traffic from mixed traffic lanes. Special attention was given to designing curbside interface zones at transfer points and park and ride facilities where enhanced pavement, signage, and bus bay geometry were implemented to streamline passenger movement and maintain schedule reliability. As part of the overall system enhancement, centralized control systems were developed at the operations center to monitor vehicle locations, schedule adherence, and station conditions. The system integrated with citywide intelligent transportation systems for comprehensive transit oversight. The final phase of the VIA Green Line BRT project included comprehensive testing of vehicle integration, signal coordination, fare collection systems, and emergency response protocols. Once fully commissioned, the corridor was opened for revenue service, marking a significant step forward in the region's commitment to sustainable, high-capacity urban transit infrastructure.
The Southeast Connector is a major highway reconstruction and expansion project taking place in Tarrant County, Texas, aimed at upgrading approximately 16.5 miles of transportation infrastructure across one of the busiest corridors in the Dallas-Fort Worth metropolitan area. The corridor includes portions of Interstate 20, Interstate 820, and U.S. Highway 287, serving as a critical east-west and north-south link for both commuter and freight traffic. This design-build project involves extensive demolition, earthwork, bridge construction, pavement replacement, and the addition of new general-purpose lanes and collector-distributor systems. Construction activities began with the mobilization of heavy equipment and the establishment of traffic control measures to safely maintain vehicular flow through active work zones. Initial phases involved the demolition of existing overpasses, barrier walls, and deteriorated pavement sections. Earth-moving operations followed, with mass excavation and embankment fills to realign roadway grades and prepare for widened sections. Subsurface utility investigations and relocations were performed in tandem to clear the path for foundational work. Bridge construction represents a significant component of the project, requiring the erection of dozens of new overpasses and flyover ramps. Deep foundations using drilled shafts and driven piles were installed to support substructures, followed by the placement of reinforced concrete columns and bent caps. Precast concrete girders were set in place using high-capacity cranes, and bridge decks were formed and poured using slip-form paving techniques. Extensive staging was required to minimize traffic disruptions, with nighttime and weekend closures strategically utilized for critical lifts and beam placements. In terms of roadway improvements, the project includes the addition of multiple new lanes to accommodate future traffic demands, with continuous steel-reinforced concrete pavement sections designed for durability under high-load conditions. Collector-distributor roads were constructed alongside main lines to improve interchange efficiency and reduce weaving conflicts. Frontage roads were also expanded, and new ramps were introduced to facilitate better access and egress at key junctions. Drainage systems, including concrete box culverts, storm sewers, and detention basins, were constructed to manage stormwater runoff and prevent flooding. Intelligent transportation systems such as dynamic message signs, traffic cameras, and vehicle detection systems were integrated throughout the corridor to enhance real-time traffic monitoring and incident response. Sidewalks and shared-use paths were included to support pedestrian and bicycle access, aligning with broader goals of multimodal connectivity. Scheduled for completion in 2028, the Southeast Connector is poised to significantly reduce congestion, enhance safety, and support economic growth by upgrading a vital section of Texas's highway network with modern engineering solutions and long-term capacity improvements. For decades to come, the 2nd Avenue Subway Phase 2 is the continuation of one of the most complex urban tunneling and mass transit expansion projects in the United States, aimed at extending the Q line from 96th Street to 125th Street in East Harlem. This phase includes approximately 1.5 miles of new twin-track tunnels and the construction of 3 new underground stations at 106th Street, 116th Street, and 125th Street. The engineering challenge is immense due to dense urban development, existing subsurface utilities, aged infrastructure, and the need to maintain uninterrupted city function during all phases of construction. The process begins with utility relocation, which is the most invasive and critical early task. Engineers must identify, reroute, and in some cases temporarily suspend operations of numerous existing utilities, including water mains, gas pipelines, electrical conduits, steam lines, and communications cables. This operation requires trench excavation along the length of 2nd Avenue and adjoining cross streets, followed by the installation of new reinforced conduits and manholes while ensuring services remain live wherever possible. Tunneling for the new segments will be completed using tunnel boring machines, which will be launched from designated shaft locations likely near 105th Street. These machines operate by using a rotating cutting head to break through rock and soil, while a conveyor system removes the excavated material. Behind the cutting head, the TBM installs precast concrete lining segments to create a finished tunnel wall. The twin tunnels are typically about 22 feet in diameter, allowing for safe clearance and space for walkways, conduits, and ventilation systems. Station construction will be executed using both cut and cover and mining techniques. At 106th and 116th Streets, the stations will likely be built using a cut and cover method, which requires deep trench excavation and the installation of temporary decking to allow traffic above to continue. These station boxes will be heavily reinforced and include mezzanines, platform levels, elevator shafts, stairwells, and emergency egress corridors. At 125th Street, due to geological and urban constraints, the station will be excavated using sequential excavation methods, where controlled blasting or mechanical excavation forms chambers and galleries that are immediately supported with shotcrete and rock bolts. New entrances, traction power substations, and ventilation facilities are also part of the scope. Once structural work is complete, crews will install tracks, third rail, signal systems, communications wiring, and lighting. Interior finishes, including wall tiling, signage, and fare control areas, are added last. The project requires constant coordination between civil engineers, transit specialists, utility managers, and public agencies to deliver safe, modern infrastructure while working beneath one of the most congested cities in the world. Laying an undersea transmission line is an operation that combines offshore engineering, marine geology, and high-voltage electrical infrastructure into a single continuous challenge. In the case of Empire Wind 1, the transmission system forms the backbone that delivers power from the offshore wind turbines to the onshore grid, spanning seabed, shoreline, and terrestrial corridors. The design and construction of this export cable involve multiple phases, each requiring distinct sets of equipment, expertise, and environmental management. The subsea cable installation begins with a detailed seabed survey. Hydrographic mapping, magnetometer readings, and geotechnical bore samples inform the alignment of the export route. The goal is to avoid boulders, shipwrecks, ecologically sensitive areas, and existing infrastructure like pipelines or fiber optic cables. Based on these findings, the route is finalized and cable protection measures are engineered, including burial depth profiles and potential use of rock berms or articulated concrete mattresses in harder substrates. Cable manufacturing is done well in advance, with the high-voltage alternating current cables fabricated in long, continuous segments. Each cable is composed of a central conductor, typically copper or aluminum, surrounded by layers of insulation, semiconducting sheaths, metallic armor, and external jackets. These cables are spooled onto massive turntables and loaded onto cable-laying vessels equipped with dynamic positioning systems to maintain exact alignment during installation. Prior to laying, a pre-trenching or plowing operation prepares the seabed. A remotely operated plow or jetting tool creates a narrow trench into which the cable is laid in a single pass. The cable-laying vessel then feeds the cable from its deck through a guide chute while maintaining precise tension and layback control. In areas where burial is not possible, post-lay protection using rock placement or concrete mats is deployed to prevent damage from anchors or trawling. At the landfall interface, a horizontal directional drilling method is used to bring the cable on shore without disturbing the shoreline or sensitive coastal environments. A borehole is drilled from an onshore pit out to the near-shore seabed, where a receiving pit or offshore transition joint bay is located. A duct is installed through this borehole, and the cable is pulled through using a winch system, creating a continuous sealed connection from sea to land. Onshore, the cable transitions from marine-grade insulation to terrestrial specifications at a cable transition joint housed in a secure underground vault. From there, the cable continues along a buried conduit route to the onshore substation, which is often newly constructed or significantly expanded to handle the incoming capacity. The substation includes transformers, switchgear, reactive compensation equipment, and grid interconnection systems. High-voltage transformers step the transmission voltage to a grid-compatible level, while harmonic filters and reactive power equipment stabilize voltage and frequency. Commissioning of the transmission system includes extensive high-voltage testing, thermal modeling, and live energization sequences. Protective relays and fault detection systems are calibrated to ensure the system can isolate any short circuits or overloads. Once operational, the Empire Wind 1 transmission line functions as the vital conduit converting offshore wind energy into urban-scale electricity supply, delivering clean energy while showcasing the precision and coordination demanded by subsea electrical engineering. Unlike many arenas that rise from open space, the T-Mobile Arena in Las Vegas was constructed on a tightly constrained urban site, requiring deep logistical planning before the first shovel hit the ground. The initial site preparation involved extensive utility relocation, as existing storm drains, water lines, and power conduits had to be rerouted to accommodate the building footprint and its supporting infrastructure. With minimal laydown space available, construction sequencing was planned in detail to ensure materials arrived just in time for installation. The structural system relied on a hybrid steel and concrete frame. A reinforced concrete core formed the arena's vertical circulation spine and housed elevator shafts, stairwells, and mechanical risers. Around this core, a complex array of steel columns, raker beams, and trusses supported the sweeping roof and cantilevered seating decks. The roof was particularly challenging, as it required long-span trusses to bridge the open interior without intermediate columns, allowing unobstructed views from all seats. These trusses were lifted into place using synchronized crane lifts and were temporarily braced until lateral systems were completed. Within the bowl, precast concrete seating components were craned into position and set atop steel support members. The lower bowl was poured in place using cast-in-place concrete, allowing for integration of conduit chases and drainage systems directly into the slab. To ensure optimal acoustics, the interior envelope was lined with a combination of perforated metal panels and acoustic baffles, carefully arranged to diffuse sound energy and minimize echo. Mechanical systems were installed using vertical and horizontal distribution zones to maximize ceiling clearance and fan comfort. Chilled water plants, air handling units, and ductwork were located primarily above the event floor and distributed outward through high-level plenums. Special attention was given to integrating smoke control zones, emergency exhaust fans, and CO2 sensors into the overall HVAC design. Electrical systems featured redundant feeds, backup generators, and an extensive network of lighting control nodes to accommodate both performance and broadcast demands. The arena's exterior featured a curved facade made up of glass curtain wall, aluminum panels, and exposed structural elements. These were installed in phased sequences, using mast climbers and boom lifts to operate within the spatial limits of the surrounding development. Water infiltration protection was handled using rain screen design and perimeter sealant systems, ensuring long-term envelope integrity in the arid climate.
Starting with site selection for the Gigapop data center in Red Oak, engineers prioritized proximity to major fiber routes, low seismic risk, and stable ground conditions. Once the parcel was secured, initial development began with topographic surveys and soil borings to evaluate bearing capacity and groundwater levels. Given the data center's critical function, achieving a stable substructure was imperative. Contractors excavated to a depth of several feet, removing organic material and replacing it with engineered fill compacted in lifts. Deep foundation systems, such as drilled piers, were deployed in zones with variable soil strata to ensure long-term structural stability. The facility's footprint was laid out to accommodate modular expansion, with a steel-reinforced concrete slab on grade serving as the foundation platform. Reinforcing steel cages were assembled on site and tied into slab pours, using continuous rebar loops to enhance crack resistance and load distribution. After curing, the slab served as the base for pre-engineered structural steel framing. Steel columns and wide flange beams were anchored into embedded base plates and erected using cranes, with lateral bracing and cross members installed to provide rigidity against wind and seismic loads. Envelope construction followed with the installation of insulated metal panels for both thermal performance and security. The roofing system used a mechanically fastened thermoplastic polyolefin membrane over tapered insulation to achieve proper drainage. Roof curbs were pre-installed to support future mechanical units, while penetration points for cabling and ductwork were carefully sealed to maintain the building's energy envelope and meet FM global standards. Critical to the facility's design was its mechanical and electrical infrastructure. Redundant power delivery was achieved using dual utility feeds connected to independent switchgear systems. Below-grade duct banks housed medium voltage cables leading to unit substations, which stepped down voltage for distribution within the facility. Emergency power was backed by multiple diesel generators set on reinforced concrete pads, connected to automatic transfer switches and uninterruptible power supply systems. Each UPS module was installed within a conditioned electrical room, outfitted with fire-rated walls and clean agent fire suppression systems. Cooling was accomplished using a chilled water system with air-cooled chillers mounted on structural steel platforms outside the main building. Inside, computer room air handlers circulated chilled air through raised floor plenums, delivering conditioned air directly to server aisles. Hot aisle containment was implemented to isolate and return warm exhaust air, maximizing cooling efficiency and minimizing energy usage. Cooling system piping was routed through a looped configuration with isolation valves to allow maintenance without service interruption. The data hall itself featured anti-static raised flooring, overhead cable trays for power and fiber distribution, and seismic rated server racks bolted to the slab. Environmental monitoring systems were installed to track temperature, humidity, and particulate levels, all integrated into a building management system with real-time alerts. Security was another major focus, involving perimeter fencing, man-trap entry vestibules, biometric access control, and 24/7 surveillance. All systems were tested through integrated commissioning protocols to validate performance under simulated failure conditions. Once validated, the Gigapop data center in Red Oak went live, offering high availability colocation and cloud services in a purpose-built, mission-critical facility engineered for scalability and resilience.
The Port Arthur LNG terminal is a large-scale liquefied natural gas export facility currently under construction along the Gulf Coast in Port Arthur, Texas. This mega project is designed to transform natural gas into its liquefied state for efficient overseas transport, requiring a complex assembly of process infrastructure, storage systems, marine loading capabilities, and supporting utilities. The site spans hundreds of acres and is being developed in multiple phases, with the initial phase encompassing 2 liquefaction trains, each capable of processing approximately 6.5 million metric tons of LNG per year. The project's scope includes heavy civil works, advanced cryogenic systems, and extensive marine infrastructure, all of which demand high levels of precision and coordination. Construction began with extensive site preparation, involving the clearing of existing vegetation, deep soil stabilization using lime and cement-treated soils, and the installation of dewatering systems to manage the high groundwater levels typical of the Gulf Coast region. Excavation and grading operations ensured the site met the precise elevation and drainage requirements necessary to support the heavy process equipment and prevent flooding during severe weather events. Foundations for the massive liquefaction trains and LNG storage tanks were constructed using deep pile systems, typically involving steel pipe or precast concrete piles driven to depths exceeding 100 feet to reach load-bearing strata. Above these, large reinforced concrete pile caps and slabs provided stable bases for mounting compressors, heat exchangers, and ancillary equipment. The LNG storage tanks themselves are double-walled, full containment structures composed of inner nickel-steel tanks designed to handle cryogenic temperatures and outer pre-stressed concrete shells that offer structural protection and containment in case of leaks. Installation of the liquefaction equipment required precision alignment of turbo expanders, cryogenic heat exchangers, and gas turbines, all interconnected through high-alloy piping systems built to withstand extremely low temperatures and high pressures. Welding and non-destructive testing followed rigorous standards to ensure system integrity, particularly where thermal cycling could induce material fatigue. Marine infrastructure construction included dredging of berths and turning basins, driving of large-diameter mooring and breasting dolphins, and installation of loading arms capable of transferring LNG from the terminal to specialized carriers. Safety systems were integrated throughout the facility, including emergency shutdown valves, gas detection systems, and blast-resistant control buildings. Upon completion, the Port Arthur LNG terminal will serve as a key export hub, contributing significantly to the global LNG supply chain and demonstrating advanced capabilities in industrial-scale cryogenic engineering. The Sequoia Solar Farm is a utility-scale photovoltaic power generation facility designed to produce hundreds of megawatts of renewable energy in a desert environment. The project spans thousands of acres and involves the installation of hundreds of thousands of solar photovoltaic modules, arranged in meticulously engineered arrays to maximize solar capture and energy output across seasonal variations. Construction begins with extensive site grading and preparation, ensuring a level and stable surface to accommodate the massive racking structures. The native soil is compacted and sometimes augmented with imported fill or geotextile fabric in areas requiring enhanced stabilization. The first major task involves driving steel piles into the ground to serve as foundations for the solar racking systems. These piles are typically driven to depths of 8 to 12 feet using pile-driving rigs calibrated to maintain consistent verticality and spacing. The racking systems are either fixed tilt or, more commonly in this project, single-axis trackers. Single-axis trackers are mechanically driven systems that rotate the solar panels to follow the sun's movement throughout the day, increasing energy capture by 20 to 30% compared to fixed systems. Following racking installation, photovoltaic modules are mounted in strings, often composed of up to 20 panels per row. Technicians bolt each module to the racking frame and connect them using standardized plug-and-play wiring systems. These module strings feed into combiner boxes distributed across the site. From there, direct current electricity flows into centralized inverters, which convert it into alternating current suitable for grid use. Electrical cabling is routed in underground trenches that are excavated using trenchers or chain-driven trenching machines. These trenches are backfilled with sand or thermal backfill to ensure heat dissipation and electrical insulation. Medium voltage transformers are placed at strategic intervals and mounted on concrete pads to boost the voltage for transmission. These are connected to a substation located at the perimeter of the farm, which aggregates all power generated and steps up the voltage for injection into the regional electrical grid. To ensure efficiency and longevity, each component of the system, modules, trackers, inverters, and transformers, is monitored via a SCADA system. This system collects real-time performance data, enabling operators to identify underperforming strings, inverter faults, or shading issues due to dust accumulation. The entire farm is encircled with fencing and access-controlled gates, and interior access roads are constructed using compacted gravel to allow maintenance vehicles year-round access. Transforming one of the busiest transportation hubs in North America demands not only technical expertise, but a delicate balance of preservation, modernization, and uninterrupted operations. The Penn Station redevelopment is an undertaking defined by both its architectural ambition and the intense logistical complexity of upgrading a live rail facility buried beneath one of the most congested city blocks in Manhattan. The effort to overhaul Penn Station begins with structural enhancements below grade. The existing concourses, tracks, and platforms operate under the weight of multiple buildings, including Madison Square Garden. Any changes to circulation pathways, vertical access points, or mechanical systems must be executed within strict spatial constraints, often involving night and weekend work windows when train frequency is lowest. Structural engineers rely on advanced 3D modeling and building information modeling systems to coordinate the dense layering of utilities, columns, HVAC ducts, fire suppression systems, and passenger circulation zones. One of the first technical priorities is the relocation and upgrading of aging mechanical and electrical infrastructure. High-voltage feeds, signal cabling, and ventilation shafts are rerouted through newly created utility corridors designed to accommodate future capacity and ease of maintenance. These corridors often require underpinning of adjacent foundations and careful bracing to prevent soil movement during excavation. In several locations, jet grouting and soil freezing methods are used to stabilize the ground before deep cuts are made beneath active rail beds. At platform level, modifications target the improvement of passenger flow, accessibility, and egress capacity. New elevator shafts and widened staircases are inserted through cutouts in the existing slab, reinforced with steel framing and temporary shoring during the coring process. The platforms themselves are resurfaced with high durability, slip-resistant materials, and edge warning strips compliant with current accessibility standards. New wayfinding signage, audio systems, and tactile floor indicators are integrated throughout to improve user navigation and safety. Above ground, the redevelopment includes the construction of new headhouse structures that serve as public-facing entry points to the station. These involve excavation for new foundation systems, often using drilled shafts or micropiles to thread through dense subterranean infrastructure. Superstructures are composed of steel framing and glass curtain wall systems, engineered for maximum daylight penetration and designed to bear dynamic loading from foot traffic and potential roof equipment such as photovoltaic arrays or emergency generators. To address capacity and improve commuter experience, mezzanine levels are expanded, requiring significant reconfiguration of load-bearing elements. New concourses are built with post-tensioned concrete slabs suspended over active track beds using a sequence of cast-in-place pours and pre-assembled rebar cages. Work zones are isolated using sound and dust barriers, with negative pressure ventilation systems ensuring air quality for both workers and travelers. All construction phases are coordinated with rail operators and emergency services. Detailed construction staging plans sequence deliveries, waste removal, and equipment installation into narrow time slots between train operations. Emergency egress routes are continually maintained and adjusted as interior spaces evolve. The redevelopment culminates in a completely modernized Penn Station environment, mechanically efficient, structurally sound, and navigable at volumes exceeding several 100,000 passengers per day, executed entirely while the existing system remains in full operation. At the outset of the MSG Sphere's construction in Las Vegas, the most immediate challenge was establishing a foundation capable of supporting a structure unlike anything previously built. The sphere's extreme diameter, spanning over 500 feet, and height exceeding 300 feet, necessitated a ring of deep foundation caissons. These caissons, drilled dozens of feet into the caliche-laden desert subsoil, provided load-bearing support for the concrete mat foundation that would carry the entire dome. Crews installed dense rebar cages and tremi-poured concrete in segments, ensuring continuous integrity under the enormous compressive and lateral loads. The frame of the sphere was formed using a hybrid structural system combining concrete cores with an extensive steel diagrid shell. The steel members, many of them curved and custom fabricated, were craned into place with extreme precision. Each joint had to accommodate subtle geometric variances in the spherical curvature, requiring extensive use of laser surveying and point cloud modeling during assembly. The use of node connectors, each one custom engineered, allowed thousands of steel segments to interlock into a stable geodesic structure. Work progressed concentrically, rising from the base upwards, forming a self-supporting lattice that grew in stages toward closure at the apex. Internally, the complexity intensified. The sphere's defining feature, its fully immersive LED display surface, required a compound curved interior supported by catwalks and rigging systems hidden behind the paneling. This interior surface included more than 100,000 square feet of high-resolution LED panels. Engineers had to account for thermal expansion, cable routing, and precise angles of incidence for projection mapping and acoustics. To achieve truly immersive sound, an advanced beam-forming audio system was suspended behind acoustic mesh panels, calibrated to direct audio precisely to each seat using an array of over 100,000 speakers and transducers. Externally, the sphere's envelope was sheathed in an exoskeleton clad with LED modules designed for all-weather performance. These panels were mounted using modular aluminum frames anchored directly to the diagrid steel. Wind loading, thermal cycling, and desert dust all influenced the choice of materials and mounting systems. Throughout the build, access was achieved with a mix of suspended scaffolds, articulating lifts, and perimeter ring cranes. Construction sequencing had to account for limited laydown space and active coordination with surrounding infrastructure. With the Las Vegas Strip nearby, noise restrictions, traffic control, and night work all shaped how the project advanced. The MSG Sphere stands as a demonstration of digital architecture converging with structural audacity, where immersive entertainment dictated the blueprint from foundation to facade.
Development of the Epic City project in Collin and Hunt counties began with an immense coordination effort across municipal boundaries, utility providers, and transportation agencies to ensure the foundational infrastructure could support the scale of this master-planned smart city. The first phase focused on land grading and hydrological management across several square miles of former farmland and low-density residential plots. Large-scale earth-moving operations utilized GPS-controlled bulldozers and motor graders to establish consistent elevation profiles for future roadways, drainage basins, and utility corridors. Extensive stormwater detention systems were constructed before any vertical development began. This included the excavation of retention ponds lined with clay and geotextile membranes, along with underground box culverts installed beneath arterial roadways to channel runoff to centralized treatment zones. Detention basins were designed with multi-stage outlet structures to regulate discharge rates during both minor and major storm events, protecting downstream ecosystems and adjacent urban infrastructure. The backbone of Epic City's build-out was its underground utility infrastructure, which included triple duct banks for electrical distribution, multi-conduit telecom pathways, and high-capacity water and sewer mains. Utility corridors were installed in coordinated trenches with separate elevation layers to avoid conflicts, and all infrastructure was mapped using RFID and GIS systems for ongoing asset management. Natural gas lines were routed with cathodic protection and above-ground isolation valves to enhance long-term safety and maintainability. The transportation grid was built from the ground up to support both traditional traffic and autonomous vehicle networks. Arterial roads featured full-depth concrete pavement with doweled contraction joints and integrated sensor arrays embedded at intersections to monitor vehicle flow and environmental conditions. Roundabouts, smart traffic signals, and vehicle-to-infrastructure communication beacons were included as part of the intelligent transportation system deployment. Dedicated lanes for high-occupancy vehicles, electric buses, and autonomous delivery pods were constructed alongside main boulevards using contrasting pavement materials for clear lane identification. Vertical construction followed a hybrid model of traditional steel and concrete buildings and modular prefabrication. Commercial and civic buildings were erected using steel frames and precast concrete panels, while some residential structures utilized factory-assembled wall panels and floor cassettes to speed construction cycles. Building foundations incorporated post-tension slabs in high-traffic zones and pier-supported grade beams in areas with variable soil profiles. Each district of Epic City was designed with integrated energy systems. Distributed energy resources such as rooftop solar, battery storage, and thermal energy networks were connected to a centralized microgrid, allowing for localized energy balancing and off-grid operation during outages. Substations were constructed with switchgear housed in blast-rated enclosures, and each neighborhood included EV charging stations integrated into the sidewalk infrastructure. Water reuse systems were embedded into the municipal plumbing network, with dual pipe systems carrying reclaimed water for irrigation and cooling uses. Smart metering, automated leak detection, and flow regulation valves enabled real-time water management across residential and commercial zones. Public realm enhancements included bioswale-lined streets, shaded pedestrian corridors, and precast concrete pavers with embedded LED lighting for wayfinding and safety. All components were coordinated through a centralized digital twin of the city, allowing planners, engineers, and operators to visualize, monitor, and manage the complex infrastructure in real time as Epic City rose from concept to livable urban reality.
The Northeast Lakeview College expansion in New Braunfels represents a major investment in regional higher education infrastructure, aimed at addressing increasing enrollment demands and enhancing accessibility for students across Comal County and surrounding areas. This project involves the comprehensive renovation and adaptive reuse of a pre-existing 58,000 square foot commercial structure, formerly occupied by a financial institution, into a fully functioning academic center designed to support a broad range of instructional programs and student services. Construction activities commenced with selective interior demolition to remove non-load-bearing partitions, obsolete mechanical systems, and outdated finishes. This was followed by structural assessments to ensure the existing building shell could accommodate new loads introduced by academic programming. Reinforcement of floor slabs and roof structures was carried out where necessary, particularly in areas designated for heavy equipment such as laboratory installations and mechanical units. Mechanical, electrical, and plumbing systems were entirely overhauled. A new rooftop HVAC system with variable air volume controls was installed to ensure optimal thermal comfort and energy efficiency across diverse instructional spaces. Electrical upgrades included new panel boards, LED lighting fixtures, and structured cabling to support campus-wide Wi-Fi and integrated classroom technologies. Plumbing infrastructure was expanded to serve additional restrooms, science labs, and break areas, with low-flow fixtures and hot water recirculation systems incorporated to reduce water consumption. Interior build-out included the construction of general-purpose classrooms, computer labs, science laboratories with fume hoods and gas piping, faculty offices, and multi-use student spaces. Specialized instructional areas were outfitted with flexible furnishings, audio-visual systems, and digital teaching tools compatible with hybrid learning formats. Acoustical treatments such as suspended ceiling panels, wall baffles, and sound-isolating doors were used throughout the facility to maintain a conducive learning environment. Accessibility upgrades brought the building into compliance with the Americans with Disabilities Act, including the installation of a new elevator, widened doorways, tactile signage, and accessible restroom facilities. The entry and exit points were redesigned with automated doors and weather protection canopies, and site work improvements included new sidewalks, AD-compliant parking, landscaping, and stormwater management systems. The project also involved the addition of a new fire protection system, including sprinklers and a fire alarm network, fully integrated into the college's safety protocols. Security enhancements included controlled access points, surveillance cameras, and emergency communication systems. Once operational, the expanded Northeast Lakeview College campus in New Braunfels will serve as a vital educational hub, providing state-of-the-art facilities and instructional capacity to support the growing academic needs of the region. Brightline West is a high-speed rail project under construction with the goal of connecting Las Vegas, Nevada to Rancho Cucamonga, California. Designed to reduce vehicle congestion on the I-15 corridor, the system is being engineered for electric trains capable of operating at speeds up to 200 miles per hour. The entire route spans approximately 260 miles and is being built primarily within the median of the I-15 highway, which presents unique logistical and structural engineering challenges. The first major phase of construction involves extensive right-of-way preparation. Since the alignment runs along an existing highway corridor, engineers must stabilize soil and regrade the median to accommodate double-track guideways. Excavation equipment is used to dig trenches and remove unsuitable soil, which is then replaced with compacted aggregate layers to form a solid base. Drainage systems are installed concurrently to prevent water accumulation and erosion beneath the future track. Concrete slab track construction is favored over traditional ballasted track due to its lower maintenance requirements and stability at high speeds. Precast or cast-in-place concrete track beds are laid with precision alignment to maintain tight tolerances for rail geometry. Continuously welded rail is installed atop these slabs using embedded fastener systems, which reduce vibration and noise while securing the rails rigidly. Bridge structures are required at various highway interchanges, flood zones, and wildlife crossings. These are built using deep foundations, such as driven piles or drilled shafts, with superstructures formed from precast concrete girders or cast-in-place box segments. Temporary falsework and heavy cranes are used extensively during this phase to hoist components into position. Stations are being designed with elevated platforms, intermodal access, and parking structures. Construction here includes deep excavation for utilities, elevator shafts, and escalator systems. Steel framing and curtain wall systems form the structural and architectural envelope of the terminals. Power delivery is achieved through an overhead catenary system. Substations convert utility power to the necessary voltage for high-speed traction. The catenary poles are installed at regular intervals with tensioning devices to maintain wire elevation and consistency. The replacement process began with a comprehensive assessment of hydrological patterns along the Tugneoga River. Engineers conducted hydraulic modeling to determine the appropriate bridge height and span length that could withstand a 100-year flood event. River scour, which had contributed to undermining the older abutments, necessitated special attention in the design phase. To counteract this, deep foundation systems such as driven steel piles and reinforced concrete caissons were specified to anchor the substructure well below the scour depth. Construction sequencing had to be carefully planned to maintain traffic flow. In many such cases, a temporary detour structure or a stage construction method is adopted. Here, stage construction allowed half of the bridge to be built while traffic continued on the remaining half, supported by temporary shoring and reinforced decking. This minimized disruptions to local communities and commercial routes. Demolition of the old bridge structure required systematic deconstruction, starting with deck removal followed by segmental dismantling of girders and piers. Environmental controls were deployed to prevent debris from entering the river, including floating turbidity curtains and debris nets. Once cleared, work commenced on the new foundations, which included cofferdams constructed from interlocking sheet piles to isolate work zones from the water and create a dry workspace for excavation and concrete placement. The superstructure was designed as a multi-span steel girder bridge with composite concrete decking. High-performance weathering steel was chosen for the girders to reduce long-term maintenance by forming a protective oxide layer. The concrete deck was poured over galvanized stay-in-place forms with integral shear studs to create a composite action between the steel girders and the concrete slab. Expansion joints and neoprene-bearing pads were incorporated to accommodate thermal movement and live load deflection. The bridge rails and parapets were upgraded to meet current crashworthiness standards, employing reinforced concrete barriers with a steel rail on top. Drainage features were integrated into the deck design to channel water away efficiently, reducing the risk of icing in colder months. Roadway approaches were reconstructed with improved alignment and transition zones, incorporating guardrails, pavement striping, and signage to enhance driver safety. Throughout the project, geotechnical instrumentation monitored settlement and lateral movement, ensuring foundation integrity as loads transferred from the superstructure. Final inspections included load testing, visual surveys, and non-destructive evaluation methods such as ground-penetrating radar and ultrasonic testing of welds. Upon opening, the new Tioughnioga River Replacement Bridge represented not just a physical crossing, but a renewed commitment to infrastructure longevity and regional mobility, crafted through rigorous engineering and carefully managed construction logistics. Shifting focus to one of the most significant sports construction projects in recent American history, Allegiant Stadium in Las Vegas began with an enormous excavation effort to prepare the site just west of the Strip. The soil conditions required pre-treatment due to high water tables and loose granular fill. To stabilize the subgrade, contractors used deep soil mixing and installed wick drains to accelerate consolidation. Once the pad was secured, work commenced on the foundation, which incorporated hundreds of drilled piers and massive concrete footings to support the superstructure. The building's primary frame featured a combination of steel trusses and precast concrete components. One of the defining features of the stadium, the sweeping roof canopy, was enabled by a network of long-span steel trusses, each weighing several hundred tons. These elements were fabricated off-site and delivered in sequential shipments, where they were assembled using gantry cranes and specialized rigging equipment. The roof itself was a cable-supported ETFE system that demanded meticulous tensioning and anchorage precision to accommodate thermal movement and wind uplift. Inside, the seating bowl was configured with precast raker beams and vomitory walls, each piece carefully aligned to maintain sightlines and support tiered loads. The lower bowl was cast in place, while the upper levels were constructed using a combination of steel risers and precast planks. Mechanical systems were housed in interstitial levels between the concourses and integrated into the structure to reduce noise and vibration transmission. One particularly ambitious component of the project was the operable field tray. Designed to support natural grass for NFL games, the tray rested on a series of rails embedded in the foundation slab. It could be rolled in and out of the stadium using hydraulic motors and steel wheel assemblies, weighing several million pounds in total. This required structural coordination with the surrounding apron and subgrade drainage systems, which had to accommodate both static and dynamic loads without settlement. Facade construction involved a high-performance curtain wall system clad in black fritted glass and metal panels. Behind this outer skin, wind bracing and thermal barriers were integrated to manage the desert climate. Each section of the envelope was panelized off-site and installed via mobile cranes in a rapid sequence, closing in the building in time for interior finishes to commence. Allegiant Stadium represents a convergence of speed, scale, and innovation, completed on a fast-track schedule that demanded round-the-clock coordination across hundreds of trade contractors.
Construction of the Texas State Highway 365 tollway began with extensive site surveying and environmental assessments, given the area's sensitivity to both hydrological patterns and existing urban developments. Civil engineers first conducted geotechnical studies to determine the bearing capacity of the soil, as large portions of the alignment traversed alluvial plains with variable subsoil conditions. These studies inform the design of the subgrade and the depth of excavation required to create a stable foundation for the tollway structure. Once site clearing began, vegetation was removed, utilities were identified and either relocated or protected, and temporary erosion and sediment control measures were installed. Bulldozers, graders, and excavators were deployed in a phased manner to strip the topsoil, cut into embankments, and level the terrain. Given the proximity to flood-prone regions, extensive drainage infrastructure was integrated early in the grading process. This included the installation of reinforced concrete box culverts, precast stormwater inlets, and longitudinal storm sewer systems to manage runoff and prevent roadbed saturation. Next, the base layers were constructed. This began with the application of a geotextile fabric over weak subgrade areas to enhance load distribution. Crushed limestone was brought in and compacted in layers to create a high-density, non-expansive base that would support the weight of the pavement structure and vehicle loads. For quality assurance, Nuclear density gauges and Proctor tests were used regularly to verify compaction levels. Concrete paving was selected for most of the tollway due to its longevity and load-bearing capacity. Slip-form pavers were employed to place continuously reinforced concrete pavement. This process involved laying down steel reinforcement, followed by the extrusion of concrete slabs, which were then textured and cured to ensure strength and skid resistance. Joints were carefully sawed at intervals to control cracking, and curing compounds were sprayed to prevent premature moisture loss. Parallel to the mainline construction, interchanges and ramps were built to facilitate connections with existing highways and local roads. These structures required drilled shaft foundations, formed and poured reinforced concrete columns, and precast concrete beams or steel girders, depending on the span and clearance requirements. Falsework and shoring systems were meticulously planned to support these structures during the erection phase, ensuring alignment and stability prior to concrete deck pours. Tolling infrastructure was integrated using overhead gantries equipped with electronic transponders and cameras. These systems were supported by underground conduits for power and fiber optic communication, which were installed prior to paving to avoid later disruption. Intelligent transportation systems, including variable message signs and traffic monitoring sensors, were installed along the corridor to support dynamic tolling and real-time traffic management. Safety features such as guardrails, crash attenuators, and high-mast lighting were implemented throughout the corridor. Landscaping and revegetation of disturbed areas helped control erosion and restored the environmental buffer along the right-of-way. Once construction was substantially complete, final striping, signage, and pavement marking were applied, and punch list items were addressed before the tollway was open to the public.
The East Blackland Solar Project, located in Travis County, Texas, is a utility-scale photovoltaic power generation facility designed to harness solar energy through the deployment of high-efficiency solar panels across several hundred acres of land. The project is part of a broader strategy to expand renewable energy capacity in Central Texas and contributes to grid reliability and emissions reduction targets by providing clean electricity to the regional power market. Construction of the facility began with comprehensive site assessments to evaluate solar irradiance, soil stability, drainage patterns, and potential environmental impacts. Land preparation included grading to create a uniform slope for optimal panel alignment, followed by the installation of erosion control measures, such as silt fences and retention basins to manage stormwater during construction. Once the site was cleared and stabilized, trenching operations commenced to lay underground conduit for power and communications cabling, which would later connect the solar arrays to inverters and switchgear. The racking systems, which support the photovoltaic panels, were constructed using galvanized steel posts, driven into the ground at regular intervals. These posts were installed with hydraulic pile drivers calibrated to maintain precise verticality and depth. The project utilized single-axis tracking technology, which allows solar panels to follow the sun's path across the sky, thereby maximizing energy production. The tracking systems were assembled on the support structures and equipped with actuators and controllers programmed to adjust panel tilt based on real-time solar position data. Photovoltaic modules were mounted in rows on the racking systems with electrical connections made in series to form strings, which were then aggregated into combiner boxes. From there, direct current electricity was routed through underground cables to centralized inverter stations, where it was converted into alternating current. Each inverter station included transformers, switchgear, and protective relays designed to manage voltage regulation, grid synchronization, and fault protection. A high-voltage substation was constructed on site to step up the electricity to transmission-level voltages and interconnect it with the local utility grid. This substation included power transformers, circuit breakers, and transmission line takeoff structures, all built to utility specifications. The entire site was enclosed with security fencing and equipped with monitoring systems, including weather stations and real-time data acquisition platforms that allow operators to track performance metrics and remotely manage the system. Upon completion, the East Blackland Solar Project became a key renewable energy asset for the region, demonstrating the scalability and reliability of solar technology in utility applications and supporting the ongoing transition toward a more sustainable energy infrastructure. Sound Transit 3, often abbreviated as ST3, is a massive, multi-decade transportation infrastructure expansion project in the Seattle metropolitan region. It builds upon the earlier SoundMove and ST2 initiatives by significantly enlarging the regional light rail, bus, rapid transit, and commuter rail systems. The centerpiece of ST3 is over 60 miles of new light rail lines, which are being developed through phased construction efforts extending into the 2040s. The construction process begins with corridor identification, environmental impact studies, and community consultations. Engineers perform geotechnical surveys using boreholes and core sampling to understand subsurface conditions. Once the alignments are finalized, utility relocation takes place. This involves rerouting water, gas, electric, and telecom lines that intersect proposed trackways and stations. Earthwork follows with excavation and grading for at-grade segments, and tunneling operations initiated for underground portions. For tunnels, tunnel boring machines are deployed, often starting from launch pits constructed at key portal locations. These machines advance slowly, installing precast concrete segmental linings as they progress. For elevated rail, large-diameter drilled shafts and pile foundations support cast-in-place or precast segmental bridge spans. These elevated guideways are assembled using cranes and form travelers, depending on span length and urban constraints. Simultaneously, construction of maintenance bases and operation control centers is undertaken. These facilities are critical for housing rolling stock and coordinating train operations. Station construction is another vital component, with excavation, foundation pours, steel erection, and architectural finishes being executed in sequence. Many of these stations are designed to integrate with bus transit, biking facilities, and pedestrian infrastructure. Track lane includes concrete plinth or ballast track construction, depending on whether the line is underground, elevated, or at grade. Overhead catenary systems are installed for electric traction alongside signal systems, communication cables, and substations for power distribution. ST3 also includes major upgrades to existing infrastructure, which involves service interruption planning, night shifts, and temporary track diversions. Every step is overseen with rigorous quality control, safety protocols, and coordination with municipal agencies to minimize public disruption. Bridges that span tidal rivers and serve both freight and passenger rail must meet an unusual combination of durability, flexibility, and navigational accommodation. The Livingston Avenue Rail Bridge, a vital crossing over the Hudson River between Albany and Rensselaer, is one such structure, and its planned replacement presents a complex interplay of structural engineering, river hydraulics, and transportation continuity. The existing bridge, over 100 years old, suffers from frequent mechanical failures and speed restrictions, necessitating a full reconstruction while preserving continuous rail service throughout the process. Replacing a movable bridge over an active waterway introduces immediate sequencing challenges. The new bridge will likely be constructed on a parallel alignment to the existing span, minimizing disruption to current operations and allowing much of the work to proceed concurrently. Temporary causeways or trestles may be used for construction access, but these must be carefully engineered to avoid interfering with river navigation and environmental constraints, particularly those related to tidal flows and aquatic habitat preservation. Foundation work begins with driving deep piles into the riverbed to support the new bridge piers. These piles must penetrate through layers of sediment and into competent glacial till or rock, requiring a combination of vibratory and impact driving techniques. In certain areas, drilled shafts or large-diameter caissons might be more appropriate due to subsurface conditions or noise constraints. Cofferdams are erected around pier locations to dewater the site and allow for dry concrete placement of footing and pier cap structures. The new superstructure will be designed to accommodate both high-speed passenger and heavy freight trains, likely employing steel through girders or a deck truss configuration to balance strength and span length. Modern design codes require larger live load allowances, greater lateral wind resistance, and robust fatigue life considerations, particularly important given the bridge's expected daily use by Amtrak and other rail operators. The track structure will use continuous welded rails supported on precast concrete ties and ballast, all configured to allow smoother transitions over expansion joints and movable elements. A key feature of the Livingston Avenue Bridge is its movable span, traditionally a swing span. In the replacement design, a modern swing, bascule, or vertical lift span must be selected based on navigational requirements and clearance needs. This movable section will be driven by hydraulic or electromechanical actuators with redundant controls, backed by fail-safe locking systems and real-time monitoring instrumentation. The machinery rooms and operator houses must be integrated into the bridge profile while allowing access for maintenance and inspection. Breaking ground on the new Las Vegas Stadium project involves an immediate confrontation with both scale and site complexity. Before construction on any vertical elements could begin, civil crews undertook mass grading operations across a site encompassing dozens of acres situated near critical transport infrastructure. Excavation equipment worked around the clock to balance cut and fill volumes, and sediment control basins were installed to comply with regional stormwater regulations. Soil stabilization techniques, including lime treatment and compaction grouting, were applied in zones identified by geotechnical surveys as having potential for settlement. The structural skeleton of the stadium is expected to be a composite of reinforced concrete cores and structural steel framing, optimized to support a multi-tiered seating bowl and a retractable roof or canopy. Temporary shoring towers and formwork systems will be deployed to construct the poured-in-place vertical cores, which will house elevator banks, mechanical risers, and egress stairs. Once the cores reach adequate height, sequential steel erection will begin. This involves the staged installation of primary steel columns, roof trusses, and raker beams, using crawler cranes capable of operating at tight radii due to the constrained urban site. Simultaneously, the substructure below grade will include utility tunnels, equipment vaults, and mechanical rooms. These require waterproofing membranes, concrete admixtures for sulfate resistance, and cast-in-place slab systems with embedded sleeves for mechanical and electrical penetrations. Mechanical engineers will be installing a central chilled water plant, routing large-diameter piping through below-grade trenches and into elevated concourses through a system of vertical shafts and distribution headers. The stadium's envelope will likely employ high-performance glazing, custom aluminum rain screen panels, and photovoltaic-ready roof surfaces. These components will be supported by secondary steel framing and sealed using multiple air and moisture barrier systems. Installation of the facade will proceed from multiple elevations concurrently, using mast climbers and suspended scaffold systems. Wind bracing and lateral load transfer connections will be closely monitored during this phase using field weld inspections and survey control points. Interior fit-out will be driven by overlapping trades working in tiered zones, beginning in back-of-house service corridors and proceeding outward to premium suites, concessions, and seating areas. Audio-visual integration, including massive LED boards, arena-grade speaker systems, and real-time data infrastructure, will require extensive cable tray systems and climate-controlled control rooms. The new Las Vegas Stadium will ultimately stand as a hyper-engineered fusion of sports architecture and logistical orchestration, delivering a landmark capable of hosting international events and enhancing the city's already iconic skyline.
Across the sprawling DFW Metroplex, the emergence of hyperscale data centers began with extensive land acquisition in strategically positioned industrial parks and technology zones. These parcels were selected based on proximity to high-capacity electrical substations, dark fiber routes, and minimal exposure to flood hazards. Before vertical construction could begin, civil engineers undertook large-scale earthworks to level the terrain, compact subgrade, and construct internal roadways capable of supporting the constant delivery of construction materials, generators, and prefabricated equipment modules. With the footprint of each data center sometimes exceeding several 100,000 square feet, foundations were designed for heavy point loads, particularly under mechanical galleries and electrical rooms. Reinforced concrete mats were poured atop dense layers of engineered fill and often included embedded anchor systems for equipment skids and heavy racks. Structural steel frameworks rose rapidly using pre-assembled columns and girders, lifted by crawler cranes and joined using high-strength bolted connections. Tilt-up concrete wall panels were commonly used for perimeter enclosure, offering both speed of erection and excellent thermal and blast resistance. Roof systems were engineered with significant load allowances to accommodate air handling units and dry coolers. Steel bar joists spanned long bays, supporting a composite steel deck that received a rigid insulation layer and a fully adhered membrane roofing system. Each penetration point was pre-coordinated with mechanical, electrical, and plumbing disciplines to avoid interference and maintain weather-tight integrity. Electrical systems formed the backbone of hyperscale operations, beginning with dual utility feeds backed by on-site substations built specifically to meet the center's megawatt-scale demands. Power was stepped down through gas-insulated switchgear before being distributed via bus duct and armored cable to critical electrical rooms. Redundant, uninterruptible power supply units were housed in independent, fire-rated enclosures, with each feed isolated to maintain Tier 4 design principles. Diesel backup generators, often rated between 2 and 3 megawatts each, were installed on exterior pads with bulk fuel storage and automated day tanks. These were integrated into a site-wide power management system that allowed seamless transition during utility outages. Power distribution units and remote power panels fed rows of server racks with branch circuit monitoring for granular load balancing. Cooling infrastructure was designed for energy efficiency and fault tolerance. Indirect evaporative cooling systems, chilled water loops with centrifugal chillers, and direct expansion systems were all used depending on the operator's design preference. Cooling distribution was delivered through underfloor plenums or overhead ductwork, coordinated with containment systems that separated hot and cold aisles. CRAC and CRAH units operated in N+1 or 2 N configurations, and thermal storage tanks were added in some locations to buffer peak load conditions. Inside the white space, raised flooring was laid over pedestals anchored to the slab, allowing for airflow and cable management. Overhead trays carried fiber optic trunks, copper power conductors, and sensor cabling. Fire protection was achieved through clean agent suppression systems and pre-action sprinklers, triggered by multi-sensor detection arrays. To ensure long-term operational resilience, the commissioning process was exhaustive, including integrated systems testing and load bank simulations. As each hyperscale data center in the DFW Metroplex came online, it represented the convergence of massive power infrastructure, advanced thermal engineering, and mission-critical reliability built to serve the digital economy at scale.
The Harbor Bridge Replacement Project in Corpus Christi, Texas, represents one of the most ambitious infrastructure endeavors in the region, designed to replace the original bridge constructed in the mid-1950s. The new structure is engineered as a cable-stayed bridge, designed not only to accommodate increased traffic loads, but also to provide greater navigational clearance for maritime traffic. The new bridge will span approximately 1,661 feet across the Corpus Christi Ship Channel, featuring a main span that will be one of the longest of its kind in the United States. The project includes the demolition of the existing bridge, construction of approach roads, interchanges, and the bridge itself, which is expected to dramatically improve safety, traffic flow, and economic opportunities in the region. Site preparation began with extensive geotechnical investigations to assess subsurface conditions, followed by clearing and grading of the surrounding area to make way for construction activities. Deep foundation systems, primarily composed of reinforced concrete drilled shafts, were constructed to anchor the massive support towers of the cable-stayed span. These shafts extend over 100 feet below ground to ensure stability in the coastal environment, where soil conditions include a mix of clay, sand, and silt with high water tables. The main pylons, rising over 500 feet into the air, were constructed using high-strength reinforced concrete and required precision formwork and climbing form systems to maintain alignment during vertical construction. Simultaneously, the precast segmental approach spans were fabricated off-site and transported to the site for assembly. Each segment, weighing several tens of tons, was lifted into place using specialized launching gantries and strand jacks. The stay cables, which are the defining characteristic of the bridge's design, were installed in a carefully sequenced process to balance loads and prevent excessive stress on the partially completed structure. Each cable bundle was tensioned to precise specifications using hydraulic jacks, ensuring structural integrity and minimizing deflection. Logistical challenges included coordination with ongoing port operations, maintaining traffic flow during construction, and ensuring compliance with stringent environmental regulations protecting the adjacent wetlands and water bodies. Advanced monitoring systems were embedded within the structure to track stress, displacement, and vibrations throughout the life of the bridge. Upon completion, the new harbor bridge will not only serve as a critical transportation link, but also stand as a landmark of modern engineering achievement on the Gulf Coast. Empire Wind is a major offshore wind development located in the Atlantic Ocean off the coast of New York, aimed at delivering renewable energy directly into one of the most power-demanding regions of the United States. The project is being constructed in two phases, known as Empire Wind 1 and Empire Wind 2, together comprising several gigawatts of capacity. The wind farm is situated in the New York Bight, in a federally designated wind energy area stretching between 15 and 30 miles south of Long Island. The engineering scope of this project is immense, involving marine logistics, heavy structural fabrication, subsea electrical installation, and coastal infrastructure upgrades. Construction began with extensive marine geophysical and geotechnical surveys to assess the ocean floor. These surveys utilized sonar and core sampling to determine sediment composition, load-bearing capacity, and potential obstructions. Based on the findings, monopile foundations were selected for the turbines. These are large steel cylinders, some over 30 feet in diameter and hundreds of feet in length, driven deep into the seabed to support the massive towers and nacelles. Pile driving is conducted using dynamic hammers aboard specialized jack-up vessels that anchor to the seafloor during operations. The wind turbines, each rated at over 10 megawatts, consist of a steel tower, nacelle housing the generator and gearbox, and 3 rotor blades, each longer than a football field. These components are pre-assembled at coastal staging areas and transported by heavy lift installation vessels. Once at sea, cranes aboard these vessels lift and assemble the components in stages. First the monopile, followed by transition pieces, then towers, nacelles, and finally blades. Each turbine is connected to an offshore substation via inter-array cables buried into the seabed using jet plows or cable plows. The substations transform the voltage and transmit power through export cables back to shore. These export cables, which are also buried to protect against anchors and trawling, make landfall at pre-engineered transition points. Onshore, electrical substations are constructed to receive and further convert the power before it enters the regional grid. These substations include switchgear, transformers, and reactive compensation equipment to manage voltage stability. Simultaneously, the operations and maintenance facility is built at the port, featuring docking facilities for crew transfer vessels, storage for spare parts, and remote monitoring systems to track turbine performance in real time. Every stage is synchronized for logistical efficiency, environmental compliance, and long-term operational resilience. Rising from the arid landscape of Story County, Nevada, the Gigafactory Nevada was conceived as a cornerstone of Tesla's ambition to revolutionize battery production at an unprecedented scale. Construction began with extensive earthworks to level the undulating terrain. The site, chosen for its proximity to rail lines and major highways, required vast quantities of excavation and grading. Bulldozers and graders reshaped the desert floor, while stormwater management systems were installed to direct runoff during rare but intense rainfall events. Once the pad was prepared, engineers focused on laying the foundation. Due to the immense footprint, eventually designed to exceed over 13 million square feet, the slab had to be poured in meticulously scheduled phases. Reinforced concrete was poured in segmented pours, each with embedded conduits and anchor bolts for future equipment. The structural frame was composed of prefabricated steel columns and trusses, delivered in sequenced shipments and lifted into place with crawler cranes. Crews worked in rotating shifts to maintain continuous progress, erecting hundreds of structural bays in parallel operations. Inside, the factory's layout followed a vertically integrated production flow. Raw materials entered at one end and passed through successive stages of battery cell fabrication, module assembly, and finally powertrain integration. To support this, the building's design included wide-span bays and a column-free floor plan for maximum flexibility. Utility corridors were embedded both overhead and beneath the slab to house compressed air, process water, chilled water lines, and high-voltage electrical conduits. HVAC systems were configured to manage precise temperature and humidity tolerances essential for lithium-ion battery production. In terms of energy use, the building was engineered to eventually operate on renewable sources. Roofing was structured to support photovoltaic panels, and internal systems were optimized for energy recovery and minimal waste. Fire suppression posed unique challenges due to the chemical nature of the materials. Thus, specialized foam systems and compartmentalized fire zones were integrated into the design. Construction logistics had to accommodate a remote site with limited access roads. Materials were staged off-site and trucked in with just-in-time precision to minimize storage on the congested site. Labor coordination was also a challenge, requiring thousands of workers from multiple trades and subcontractors, all operating under tight schedules and strict safety protocols. By scaling battery production to such a degree, Gigafactory Nevada marked a shift in how energy storage systems could be manufactured, economically, locally, and with the intent of creating a closed-loop supply chain. The Waterline Tower in Austin, Texas, is an ambitious high-rise construction project that, upon completion, will become the tallest building in the state. Rising to a height exceeding 1,000 feet, this mixed-use skyscraper is engineered to accommodate residential units, a luxury hotel, office spaces, and retail areas, all within a compact downtown footprint adjacent to Lady Bird Lake. The complexity of the tower's design and construction stems from its height, slender profile, and the integration of diverse occupancy types across its vertical structure. Initial construction began with deep excavation and shoring to enable installation of a mat foundation capable of distributing immense structural loads across Austin's variable limestone and clay subsoils. Foundation work included the drilling of reinforced concrete piers extending more than 100 feet into bedrock, coupled with a heavily reinforced concrete mat that was poured in a single continuous operation, requiring logistical coordination of multiple concrete batch plants and continuous pumping over several days. The building's superstructure is composed primarily of a high-strength reinforced concrete core, which houses vertical transportation systems and provides torsional stability against wind and seismic forces. Outrigger and belt truss systems are integrated at mechanical levels to distribute lateral loads across the perimeter columns, enhancing structural rigidity. The core was constructed using a self-climbing formwork system, allowing for continuous vertical progress without reliance on external scaffolding, while steel and concrete composite floor systems were constructed simultaneously to minimize schedule duration. Mechanical, electrical, and plumbing systems are vertically stacked in dedicated shafts with strategically located mechanical floors to ensure efficient distribution and maintenance access. High-efficiency chillers, low-flow plumbing fixtures, and advanced lighting controls are integrated as part of the building's sustainable design approach, targeting LEED certification. The American Legion Bridge Replacement Project is a major infrastructure effort to replace the aging and overcapacity bridge that carries the Capital Beltway, Interstate 495, over the Potomac River between Maryland and Virginia. The original bridge, built in the early 1960s, is structurally deficient and functionally obsolete due to narrow shoulders, limited capacity, and decades of heavy use. The replacement project involves constructing a modern, wider span that increases capacity, incorporates managed toll lanes, and enhances resilience to future traffic demand and environmental conditions. The construction sequence begins with extensive site preparation on both riverbanks. This includes clearing land for construction staging areas, installing erosion control measures, and conducting geotechnical investigations. Boreholes are drilled along the riverbed and banks to determine subsurface conditions, which informs the design and placement of bridge piers and foundations. Based on these studies, deep foundations using drilled shafts or driven piles are selected to anchor the new structure into stable rock or dense soil layers below the river. To maintain traffic flow during construction, a phased approach is employed. The new bridge is constructed parallel to the existing one, with some segments being built incrementally to allow traffic to shift as work progresses. Temporary trestles and causeways are installed in the river to support construction cranes, concrete pumps, and material transport without disrupting river navigation. The new bridge design features multiple travel lanes in each direction, including high-occupancy toll lanes. The superstructure is composed of pre-stressed concrete girders or steel box girders, depending on span length and navigational clearance requirements. These girders are placed atop reinforced concrete piers that rise from pile caps anchored into the riverbed. Each pier includes icebreakers and scour protection to resist hydraulic forces and sediment erosion. Deck construction involves forming, reinforcing, and pouring cast-in-place concrete slabs with integrated expansion joints and drainage systems. Barriers, lighting, and intelligent transportation systems such as traffic cameras and electronic tolling gantries are embedded into the bridge infrastructure. Noise barriers and aesthetic elements are incorporated to meet community and environmental guidelines. Upon completion of the new bridge, traffic is shifted and the old structure is carefully demolished. This involves cutting and removing steel or concrete elements in segments, using barges and cranes to control debris and ensure environmental compliance. The final phase includes grading, landscaping, and restoring shoreline features impacted during construction, leaving a modern, safer, and more efficient crossing over the Potomac River. Where a coal-fired power plant once dominated the landscape in Moapa, Nevada, the construction of the Reed Gardner battery storage system marked a shift toward clean energy storage and grid stabilization. The first phase of the project began with demolition and site remediation. Existing utility corridors, concrete pads, and buried infrastructure from the retired power plant had to be removed or repurposed. Soil testing and grading ensured that the land met the geotechnical requirements for placing a large array of battery enclosures and associated electrical equipment. Once the site was prepared, the foundation work proceeded with a modular strategy. Each battery container, typically the size of a shipping container, rested on reinforced concrete pads designed to bear static loads while allowing thermal expansion. These pads were poured with integrated cable trenches and embedded conduits for power and control wiring. The layout followed a linear alignment to optimize airflow, simplify maintenance access, and facilitate short routing to the power conversion systems. The energy storage units themselves consisted of lithium-ion battery cells housed in steel containers with integrated fire suppression, HVAC, and thermal monitoring systems. These containers arrived pre-assembled and were offloaded using mobile cranes or forklifts, then anchored in place with structural hold-downs. Adjacent to each group of battery containers, power conversion systems were installed, which included bidirectional inverters, transformers, and medium voltage switchgear. These systems allowed the batteries to interface with the regional grid, converting stored DC energy into AC power during peak demand periods and drawing excess electricity during off-peak times. Cable terminations and system integration require detailed coordination. High-voltage AC and low-voltage control wiring were routed through separate underground duct banks to minimize interference. Grounding grids were installed beneath the entire array, bonded to each enclosure and system cabinet to ensure personnel safety and lightning protection. The site also included perimeter fencing, surveillance, and access control in compliance with NERC reliability and cybersecurity standards. A supervisory control and data acquisition system tied all battery enclosures, inverters, and transformers into a centralized control hub. Fiber optic links and programmable logic controllers enabled real-time monitoring of temperature, voltage, current flow, and system health. In addition to the core storage function, the installation featured black start capabilities and reactive power support to bolster grid stability during contingency events.